All right, let's do this thing. So, okay. All right, so when doing the schematic on, um, how should I start? Oh, you should just add the pico W. Oh, yeah. Okay, so you make everything correct in the schematic, but then the footprint is just the headers. All right, that checks out. So, all right, so let's look up pico W. How do I find it? Is this a user? I feel like that's a user submitted. That one looks way nicer than this one. But this is a pico W. But is the pinouts are different, right? But this one looks so much nicer. Whatever. Whatever. So if we just search for this hash or what? But see, that's not what I wanted to do. All right, maybe I'll just use this. Wait, why did it open the footprint? Okay. So, can we? Do I have to add a package? Oh, here we go. Camera module. Wait, hold on. Dude, what the freak? This is all junk, though. I mean, not really, but how do I just Wow, that's pretty cool, actually. Development board. Wait, there's probably a million pages. Does it have a footprint though? That's the question. View datasheet. That's pretty nice. But I want to know, so how do we... Hold on. Sun is too bright. I gotta turn away from the sun. When I was greener. You know what? Since I'm refreshing, I'm just gonna open up KiCad. We're gonna see what's going on with KiCad. Wait, I thought I did open up 8.0. Dude, hell no. Wait, let's look up. There's probably a hella bug fixes though. Oh yeah. Dude, it's so annoying that they don't have an updater though. It's literally 1.2 gigs. Whatever, we'll just do it. Hopefully it uninstalls 8 and it like... Okay, wait, let me just watch a video on easyeda. Alright.
At Full Sail, we take a unique approach to teaching the art of film.
Wait, Nick Rawls? Is that the actual guy? Okay. No, it's Raymond Hill. But you know what? It's probably... Okay, wait. Let's see if this works.
I had a lot of requests to make an easyeda tutorial.
Oh. That's kind of annoying. For now, I don't really give a shit.
And show you how to get from idea to circuit and PCB design, and then how to order the PCBs from the sponsor of this video, GLC PCB. There are already a lot of tutorials about easyeda, and that's why I never made one myself. But I gathered a few tricks and problems that I usually have with this platform, and today I'll try to make a full tutorial, start to finish, about PCB designing in easyeda. But not just that. You will also learn how to create the component layout and symbol in case that you don't have that component in the online library, how to use the labels and minimize our schematic for a better look, how to use different tools from the menu, and I'll try to explain each tool separately, what does it do and how to use it. We will also talk about preparing the PCB for STM soldering service. So let's see a full easyeda tutorial and show you how easy it is to design your boards. Make sure you subscribe and activate the bell. Also, a huge thank you to all my patrons for the support. So let's get started. Hey friends, the sponsor of this video is GLC PCB. I always had good results with their PCB manufacturer service, and you can see that on all the PCBs on this channel. But now they also have an SMT assembly service with a pick and place machine for $7. Come back. The first thing we need is an idea, and I suppose that you already have that in mind. I usually make tests for all the circuits on my breadboard in order to make sure that the final circuit will work. After that, I kind of make the connections on paper and then finally draw the schematic in easyeda. The main reason I don't use Design Spark or Eagle anymore for my PCBs is because easyeda already has all the components online, and each time another user creates a new component, it will appear in the online library, and sharing components is very useful. Okay, so now we have our idea. Let's start with the design. First, we have to go to easyeda and create an account if you don't have one. So click register, select the username, insert your email, create a new password,
Bro,
file
what
button,
the fuck?
I'll base my example on the small radio receiver board with the Arduino. So I'll name the project Arduino Radio Receiver and click the Save button. Now this will open a new schematic sheet, but as you can see, it is not saved yet. So first thing you have to do is to click the Save button. Now you could change the title and the sheet name in order to keep track. Okay, now we have to add components. On the left side, we have the Creator menu. Here we have the easyeda libraries, and we can find a few components.
Where are the downloads? The fuck is going on? Oh no, it's gonna do it like 10 times. Oh, thank God. I wonder what, like, if you were to compare the market share of free CAD to professional CAD as opposed to KiCad versus professional ECAD, I wonder. Please tell me it's going to overwrite everything.
But I usually don't use these components from here. For more online components, click the Libraries button, and here we have all the components. Now search for any component. I start with the Mega 328 chip. Okay, now very important about these results. As you can see, we have the components divided in a few groups. First, these are the components that you can find on the LCSC, and you will see a shopping cart next to it. So if you want to make sure that you will always find the component to purchase, use the components that have the shopping cart next to them. Okay, to the next group, we have the SMT components. These are components that can be used with the new SMT soldering service from GLC PCB. If you can use this component for SMT service with the pick and place machine, the SMT icon will appear on the side of the component name. If you use a component without the SMT icon, GLC PCB won't be able to solder it using the SMT service, so have that in mind. Finally, we have the user contributed group, and here we can find all the components created by other users. But if you use one from this group, make sure that you check the dimensions and the pin numbers with the datasheet of the component, because there might be errors made by other creators. Okay, so this is my chip. I select that and place it on the schematic. Now I do the same for some resistors, capacitors, and a quartz crystal of 16 MHz. Make sure of the package that you want for your components. In this case, I will use some 0402 resistors and capacitors, and you can see the package, the value and more information in the search menu for each component. All circuits will have a ground connection and at least one power connection. For that, go in the EE library on the left side, and here we have the ground and the VCC icons. So drag those to your circuit. The parts of the circuit that have the ground icon connected will be connected together. But if you have two ground icons and you change the name of one of them, they won't be connected together anymore. Now let's make a few connections. From the Tools menu, select the wire, which is the first tool. Click the first point, and then to the second point, and now these are connected one to each other. As you can see, I'm using multiple ground icons, so all these wires are the same. Okay, now we have a few connections, but we need more. With a lot of wires, the schematic will be ugly, and you won't be able to understand it. So for that, we use the labels. So now select the netport tool from the menu. Place that on the schematic, and now double-click the name and change it. I will name this, for example, Reset. Now I connect this to the first point. Then I copy the port with Ctrl-C and Ctrl-V. If you need, you can press the R key to rotate it and place it on the other side. Now make the connections. And now this part of the circuit is connected to the pin PC6 of the Mega chip without any ugly wire. So using these net ports, we can create a good-looking schematic even if we have a lot of connections. As you can see here, in one of my schematics for a project, I have a lot of connections, but we can still read the schematic because we know that the TX is connected to the TX, D2 to D2, and so on. Okay, now I have the basic configuration of the Mega chip.
I never did that, but I'm meaning to do that because, I mean, that is how they all do it.
It's square and divide my schematic into multiple parts for power, for outputs, min ICs, and so on. But now what about if you don't find the component that
Alright, let me see. How good is this? Hopefully this didn't... Okay, cool. Let's just go to fusion models in here. It's called pan tilt. Okay, so in the schematic, I forget how to do this. You do A. Yeah, you do A to add something. Oops. How do you get... What does this mean? Oh, is that the debug thing? Dude, why does it keep showing me this? I don't like this. Ask Copilot. Actually, whatever. What the hell? Where is this? Why does that never work? Okay. Holy. Okay, wait. I'm going back to EDA. Okay, so now, alright, so let's just do it in here. What project am I in? Alright, so now I gotta go off stream and find my password and save it. Okay, hold on. Okay, I think I'm good. So let's just use the website version because now I have it open. So let's just assume this is right. So then you do L for label or something like that? I don't know what that is. How do you label? Polygon? What the flick? Okay, let's just. Okay, so the strat is that we. Let me just close all this crap. Okay, so what do you do here? Okay, so now what do we need to go to our bomb. I'm gonna close this too. Dude, what the hell? This doesn't say anything. Also, alt click is gonna not do what I want. I have to be careful of that. Okay. So yeah, so this. But the thing is, okay, so all right, I'll be right back. It's not clear what you need to do here. Okay. The thing that I kind of want to get right about this is I actually want to make sure that the current that we sort of do the simulations kind of. All right, but let's just get this right. And I'm just going to get out my paper and I'm just going to do it on paper. Okay. Okay. So we have the Pico. And we have 4 digital pins for steppers. We have 2 digital pins. And technically we only need to do 1 because we kind of want the flywheels to same at the same speed, but I think it's definitely better to use 2 different ones for ESCs. Then 1 for solenoid MOSFET. And I think that that's it. Now, the main thing is coming up with all of the actual components that we are going to use. So maybe it's... And you know what's interesting is... Okay, well, let's just start going through it. So, let's just get every part. That's probably a good first step. Okay, terminal blocks. Okay, so I don't know how to do the terminal blocks because basically in the schematic, well, specifically for the schematic, you just make 2 labels called +12 and ground, and then later on, like I don't know how to do that. Then for the stepper motor drivers, the part that I'm planning to use, because I already have some, is these PCBs that I ordered, and they have whatever the standard breadboard pin, male pins on the bottom that you just plug into the breadboard, and I was hoping to use that. So similarly with the power connectors, do I just, for the motor drivers, make it like a collection of, I don't know how to do it. Oh, so there specifically is a 2-pin terminal block. So if I just look up terminal, oh yeah. It doesn't show me a picture though, right? I think actually all right, let's keep KiCad open just so that I know what's going on. I'm pretty sure in KiCad, oh, it's gonna have to do this thing all over again. Yeah, see, what's nice is that oh yeah, screw terminal 1x2. I like that. That's exactly what I wanted. So I'd put this here, and then okay, and then this is how you do nets is, I mean, I don't know how to draw it. Add wire, add bus. I don't know the difference between wire and bus yet, but junction, no connect. Oh yeah, Q is no connect. I remember that. Label, L. So this is gonna be. Is this how you do it, or is this like bad practice? Oh wait, and then ground. How do you do ground? There's a special way for ground, right? Oh wait, global label. I think you need to do this. But then this just signifies. Oh wait, and then you do X to flip it around, and then here now. Oh wait, is it P? And you use 0. Oh, okay, but this literally is. What's the difference between making? Okay. Is there even such a thing as that? So let's look up screw terminal. I wish they showed a picture. Oh, they do. Barrier terminal blocks. Screw terminal blocks. These naming is like, I don't know how anybody does anything. This is impossible, man. Yeah. Excuse me. I think it's that. Okay. Well, we can't be hung up on a whole bunch of crap. So let's just get this in there. I mean, it seems good. So now, is there, if I do P, okay, P doesn't do. Okay. Wait, so, wait, I don't understand this. Add it into its own sheet. So if I go over here, can I just copy it? I think that that does not copy what I think it does. I wish it was just an ID. Yeah, that's kind of. Oh wait, can I? If I probably should just search that up. But so if I go to pan tilt, do I do A? No, A is a zoom in thing. Place component, and I just search up this. By Himesh. And the problem is there isn't ratings on these, so hat. Wait, how do I go back to the? Wait. Wait, how do I go back to the library thing? Please tell me I didn't close it. Okay, cool. Wait, if I fix this be Raspberry Pi Pico W. And he's using the... I say let's just do it. There's no way this thing is that wrong. I mean, the pinout is certainly right. And if we go here... Okay, wait. If we go to... New... Do we want to do new, or... Okay, so if we save this... How do we make a... Okay. UPCB. Save to existing project. We're just going to call it pan tilt. I mean, it's all one board. But so now, how do I link them? I don't know if they're linked yet. To JSON? Oh, wait, I didn't want to do check nets. I want to import changes. No, keep going. Apply changes. Okay. So now we have this, and they're not labeled at... Oh, they are labeled. Okay, cool. That's pretty nice. And honestly, I wonder how hard it would be to just like completely redesign this, to just start over. I mean, like, how much work really went into making that? But you actually want to keep it modular. Well, there isn't. I mean, it's really only if the part breaks, I feel like. Okay, so we have one part down. Now we want to add another part, right? How do you file, place, symbol? Okay, you do Shift F. Okay, it's just for search. So now we need see, it's kind of weird because okay, wait. So okay, so how do we just look at? I don't think we can get a 3D. Okay, so I want to do a new project actually. Now that I'm like, or let's just do a new schematic. We're gonna Shift F. And we're just gonna do Pico. And I think one of them had a 3D. Didn't one of them have a 3D model associated with it? Is there? Yeah, that's it. Pico W no pins. How do you full screen this? I want to see this thing. Okay, so this is the Pico W without headers, and it's a pretty good model. But how do I use it? Do I just attach it to apply? No. Modify model, refresh, remove favorite. Do I just double click it? Place. You can't place it. But can I add? I can't add another column to make sure that it has a 3D model associated with it. What's a part that maybe has a 3D model? Like a 402 resistor or something? But what's like a really common part? Is this a 3D model? Oh. You can't even move these out. This thing is not as good as people say it is. I wonder if it's better in the desktop app, but I kind of doubt it. Damn, dude. ECAD is like not as good as, I don't know. ECAD is kind of all over the place. It's mainly just that there's so many parts. Okay, let's just cancel this. What about the common library? If I add like a 603 resistor. Okay, let's literally just do this. This is the whole PCB. Now, wait, where am I? This is a new project? Is that what I said? Oh, cool. Okay. So yeah, so this is sheet 1. So now I want to do file, new PCB. I feel like this is not the right flow because this is kind of an awkward flow. But then you save this to this project. Okay, save it, and then you do Alt-I. Is that what it was? And then you say no, keep going, apply changes, and then you set these as the default, and then. Okay, so what we actually wanted to do. Okay, but is there a 3D view? Fabrication tools, 3D model manager? I mean, that is what that looks like. And they... So, oh, here we go. Okay, nice. All right, so this is starting to make some sense. You have this big-ass PCB, and you have this tiny little resistor here. So wait, so I want to go to pan tilt, save it. Now I want to go to 3D. So wait, what is 2D? 2D is, okay, 2D is like that. Now how do I get out of here? Okay, right, and it's just flat. But that's fine. But so, yeah, so this is not the right footprint for us because all we want is, the the headers, I guess. So I don't know what those pins are actually. Right. I think that's what these are. And then D plus and D minus are probably the... Oh, wait, these are all USB pins, I think. Can we look at the Pico W datasheet? Does this have a table of contents? Okay, nice. Oh, what the hell? Dude, ANSYS is literally cancer, bro. Yeah. It's literally a fusion file. And what is this? It doesn't even say what this is? Or did they do the PCB design in Fusion? I'm so confused. I think that's the same link. Note that PicoW is designed in Allegro. Import script or plugin. Okay. I'm just curious what happens if I open this. I feel like it's because I didn't unzip it. I don't know if that's true or not, but like, I mean, there's only freaking 2 files in here. I don't understand how. Let me try that shit again. But what? Oh, well, I did open up a Pico W. Where the hell is this stupid thing? My guess is that it doesn't work. Okay, so wait. So then why did this thing get associated with... I don't know why extension, it never gets shown. It's like, I just want to know the file extension. Don't try to hide basic information from me. Okay, a BRD file. So I think what we need to do is like, is there an import? Let's see. Okay. File import non-KiCad schematic. All right, I don't really care. Downloads this. Okay. Interesting. Wait, but what if I go to the PCB thing? How do I switch? How do I get out of here? Oh, you have to go here and then here. Okay, and then we import from here. So they give you a PCB, but they don't give you a schematic. But that's like... Does it really even matter? Also, what is it doing? Is it somewhere? I can't tell if it's done or not. Let's try to import it with easyeda. Just see if it does anything. Well, I want to do it in the random one. So in here, file, import, image, DXF. Is that Eagle? What's up, bro? I just want to, dude, honestly, EDA is like, it's like the Wild West. It's just like so random. All right, so we have a, wait, I thought we have a test. Can't we? Okay, I want this. And, okay, let's go here. But then I also want to open up the PCB. I want to file, import. See, this is what's weird. Where are they seeing this import thing? Open. File, open. Okay. Eagle. I think it's Eagle. Please make sure that Eagle is saved in Eagle 6 and higher. A little excursion. Dude, I love this Chinese language. I mean, they have way more important shit to do. It's just so funny. Downloads, Pico. Import file. Probably just this. Let's see, did KiCad even do anything with it? That's the crazy part. See, okay, like CAD file formats, even though there's SolidWorks and Fusion and all this stuff, there are step files, and step files pretty much work wherever you're at. But the crazy thing about this is that people are designing these electronics, and it's just completely locked down in terms of exportability. I'm sure it's better now. Like, those tools are like pretty old, or I don't know. I get the sense that they're old donkeys, but I'm sure that lots of people use them, but like I get the sense that they're old donkeys. Okay. So what the hell are we doing here? Okay. So this is the thing. So now I just want to start to change this to be, we are going to add, okay, so these flags, okay, so these flags, okay, I feel like all of these work the same way in that there's just a notion of a global label, net label. I'm pretty sure that that's, what's the difference between pin and net flag? But it all goes back to Spice. I mean, it all goes back to Spice. Actually, I wonder what their simulation is like. Do they even have simulation? I'm just curious. Yeah, I mean, they have it.
Welcome back. In this
Welcome
video,
back.
I will introduce the simulation function of easyeda.
Bro, I joke, but it's like, my Chinese is fucking, I can't speak Chinese.
There are two modes in easyeda. The first mode is standard mode, which is commonly used for PCB design. Another mode is the simulation mode, which is used for circuit simulation. The simulation mode of easyeda is based on LT-Spice. If you have used LT-Spice, you can get started with the simulation mode of easyeda very quickly. If you are not familiar with the simulation, you can click here to check our document tutorial. Here you can learn about the basic concept of simulation, how to use and create simulation models, basic usage, and advanced skills. If you encounter any problems, you can ask questions in our forum. Today we demonstrate the basic operation of simulation. First, we need to switch.
Bro, I love the little rocket.
You can click here to switch.
The rocket mouse.
Or click here to switch. Create a new project. Choose an owner.
Okay, I get it. If it's LT-Spice, I get it. I've done LT-Spice. I don't need to walk through that again. LT-Spice, dude, I don't like Spice, man. I think Spice is like overrated. Okay, so here's what we're gonna do. We're gonna do Shift F, and then it brings up the library. Then we're gonna look up. We're gonna go to My Libraries. No, what? I thought there was a standard. Oh, LCSC. Yeah, that's so cool, man. I mean, the crazy thing about this that's so different than, you can't change the width of this. That is such bogo. That's such bogus. All right, whatever. I mean, there's got to be a way, dude. How do you can't move this in? It's crazy how much information they have about these parts, though. I mean, nothing about the manufacturer is built into. I mean, that's why easyeda really is way better. Is because you have user footprints. You know, just a database of a bunch of people's hard work. And I mean, it's like, yeah, it's kind of silly. I mean, to have no Thingiverse equivalent for CAD until now. And then the other thing is, obviously, which is even more, is the parts, having the parts. But so we're going to go into here, and we're going to screw terminal, and then it gives you a tiny little thing here. So 3-pin, 2-pin. And I like that it has that. And it has the little shopping cart, so I can actually buy it. So, look, and they have 15,000 of them. See, I don't know. Is it SMT? Can I... So if I click on this, it should open up... Wait, it might open up Chrome. I might have to set my... Wait, can I just copy, view datasheet? This is going to open in Chrome, I think. Or it just doesn't do anything. Okay, whatever. So let's place this thing. So we do this. Then this is Can I rotate it? Okay, I can rotate it. Okay, wait. Let's do it. Let's do it. I mean, no. This is the best way to do it. I mean, I kind of wanted to practice the. Okay, now if we Oh wait, I did. First off, I did this back. I mean, it doesn't really matter, but wait. If I wanted to do this, it'd be like this, right? I'd do. Yeah, you would do this, right? And then you would put a wire between these. Why does that feel wrong? That doesn't feel right. But whatever. Okay, so we go here. Import changes. Oh, save it. Since I'm all using the common library parts, okay, this is what I wanted, actually. Okay, I didn't even think that, but let's just do this. Yeah, check the nets. What's wrong with this? Incomplete net. What? The complete net should contain 2 or more pins. Honestly, I don't really get it. I think that this is fine. So wait, let's close this. Tools, design, convert schematic to PCB. Just keep going. Yeah, that's fine. Okay, so now, oh, is this? Did they recommend I do this? So okay, so this is literally just the whole thing. Wait, how did I design the PC thing? Yeah, so what I actually would want to do, I think, is you you do VCC here. Okay, then you put a wire here. How do you do wire? I thought wire was like, oh yeah, it is. You put a wire to here. Oh, I guess you can't. Then you do this. Then you do this. And then you do this. So now I go design, update PCB. Please save your file. Dude, why isn't there autosave? I think I just oh, you know what? I don't think KiCad has autosave either. Oh, and it didn't give me that warning anymore, I think. Or maybe that's just because I don't really know what happened. But so now for this PCB, we should just be able to do this. Is that it? I can't tell if there's actually a trace there. I'm guessing there is. Does it tell you? I forget. Does it tell you if you haven't satisfied this schematic? It probably does. I mean, it knows where the traces are. Okay, so let's save this. And let's look at the 3D. So is it gonna, it's not gonna tell me that there's like an interference there? That's actually pretty wild. I wonder if you can like take this file and check if, so let's file, can I export the PCB as like a step file? Let's see. Wait, can I look at their docs? Dude, they actually have, oh, Control K, search. Oh, nice. Dude, they actually have good docs. Oh, nice. Wait, there's no docs. Wait, what happens if I go to 中文? Oh, they don't have it either. Okay. All right, fine. Easy. I'm just gonna Google it. Yeah, because I'm pretty sure that you can export a step file. Wait. Wait. If I go back to this. Wait, what if I just go to the PCB? Oh, there you go. Okay. See, that's kind of awkward, but yeah, that's fine. An OBJ file I'm fine with. All right, so just put it here. Nice. Dude, Electron, bro. Everyone's on this Electron thing. Okay, so why has nothing replaced Electron? We need Rust, bro. Okay. Export, extract all. So now I want to just open this in oh, this is a material file. I didn't even know that was a thing. Can't I just open this in Print 3D? Dude, that's so cool. Wait, can't I just associate? Oh, nice. Downloads, this. Okay, cool. And then what is that? Wait, can I open this with... Oh, that's funny. Can I open this with just VS Code, or is OBJ like a... No, it's text. It's a readable format. Okay. I don't know what it is, but... Launch 3D Builder? Did they write their own CAD? Yeah, that's so funny. That's hella funny. Okay. Thin walls. What is that? Wait, but where is the resistor? That's sort of my question. Okay, so wait. Okay. Let me ask ChatGPT then. If I have an OBJ file and, well, basically, I exported my PCB as a 3D model from easyeda, and I intentionally made a circuit where two of the parts intersect. So there's basically a resistor inside of a two-pin screw terminal, and basically I wanted to know, and I was able to get an OBJ file, and I wanted to know if there was a way for me to programmatically test for like this intersection. So what is an OBJ? It's a mesh. So it's not like step, because step uses like NURBS or something, right? Step file has like geometric primitives, I think. Dude, some guy came in here and just ranted about how fucking brutal step is. But they leave it in because it's like, yeah, I mean, it does suck. Oh yeah, see these B rep. I don't know what they are, but I've seen them. I mean, like yeah. So they are different. So we can close this. So now we want to check. So wait, but actually, What if I just open this thing up in my 3D printer? I'm pretty sure if I just open up Bamboo and I try to print this, but well, maybe what we'll do is God, these things are such side quests, but it's like, I just want to know what's going on. Like, I feel like if I don't know what's going on, I'm just like upset. Like, is that resistor actually in there or not? I don't even know. I mean, I could just change it, but so what do I want to do? I want to go to this downloads, and then I want to open this thing, and it might be like, okay, yeah, that sounds fine. So okay, unable to print multiple. Okay, so one thing that's funny is that there's color in this mesh. So it's more of a graphics format. But then I want to look at the bodies. Is there, oh yeah, objects. There's just one object. 51 non-manifold edges. Okay, so it fixed it. Oh, cool. Oh, nice. Okay, so flat planes are definitely not manifold. That actually makes sense, right? How do you actually test for if a... Okay, so I just want to ask. I loaded the OBJ into Bamboo Studio, and it said like 51 non-manifold edges. What does that mean, and how do they test for it? Because I actually did make a note that there was basically what looked like a flat plane that represented the top face of the PCB, and when I clicked the repair button in Bamboo, it went away. Yeah, I just want to know, what is it? Non-manifold edge is a term that refers to an edge shared by more than two faces, or an edge that belongs to only one face. Ah, an edge that only belongs to one face. Wait, but I don't understand an edge that is shared by, oh, more than two faces. Yeah. Yeah, that would be weird, right? How does that work? Yeah. That's really strange. Okay. Okay, but I don't... Alright, so whatever. I feel like I have run that course. So let's just move this out here. And then view the 3D again. And it's there. Cool. So now, is there... I know simulation, but there was a guy that like EMF. Is there actually? I think Fusion might have. Are there any ECAD tools that are? Are there any ECAD tools that will basically let me simulate whether or not the like the heat, but also whether or not it will break, because I have a circuit where parts of it need to have like 15 amps going through it, and I know that you have to be careful with a PCB that has that much current going through it. Dude, ANSYS, bro, what the heck? SolidWorks? Fusion has it. Oh, KiCad. Open EMS. Yeah, I saw that. But I never watched the video. But I don't know if this actually does claw stem. That looks pretty sick. Whoa. Bro, that's insane. 60 gigahertz? I mean, I guess it's kind of frequency independent in a way. Because that's probably simulating like a nanosecond or something. Open source energy management? Is that what that is? But, oh, to design antennas and PCBs. All right, let's just design the PCB. I'm wasting freaking time. We just want to... And then I'm just going to do it on... Yeah, yeah. Well, the layout will help with the soldering, but, like, not that much. And then the other thing I'm kind of worried about is I know that the MOSFET legs can handle the 10 amps because no one would design a package where the part they're making has a maximum current of lower than what the package can handle. So, but I don't know if those terminal like IC holders can do it. Like if you just look up okay, wait, I'll just ask ChatGPT what to look up. If I want to what should I look up on Amazon for? Basically, I have a MOSFET in my circuit, but if the MOSFET burns up or something, I want to be able to replace it. What is that part that you put in your circuit so that you just like push it in? What should I search up? T. Is that that seems like a highly specific thing. I mean, that seems like that seems like pretty specific because just look up MOSFET holder. Yeah, in a way, that's like better because they already designed it. Okay, what was it called? T-O... Oh, T socket. Yeah, right. So, like, if you look at these, it doesn't actually tell you the current rating, typically. Yeah. And if I just look up MOSFET socket... That was the one we just looked at. I don't know. That's the crazy thing. Well, what if we just Google TO220 socket? And we just look at... But, like, maybe I'm... That's such a crazy thing to say. It's still just for humans. That's so interesting. Okay, so wait, IC sockets, 17,000 items. Oh, socket adapters. Yeah, dude, the part classification's so interesting. Okay, wait, so can we sort by... Wait, this is the part. Series is a TT... TO... S... What about 220? Is 220 in there? 220 is not in there, so I don't know what series means. Packaging... The interesting thing for me is like why. Okay, so wait. Let's just take one of them and see if it actually has a data sheet because I mean these things must have a specification of current, right? Yeah. Here you go. See contact current rating, 1 amp. That's what I'm saying, bro. That's what I'm saying, man. So then, like, what if I just search up 10 amp TTO 10A TO220 socket? Yeah, see this exactly. And the only reason why I'm hounding this is because, like, actually, no. Let's see. Presumably, the screw terminal blocks are rated for high current. I'm pretty sure they are. I think I actually remember looking that up on stream. Uh, so what else is in the circuit? All right, can we just like? Okay, so can we just do this, bro? I'm getting so distracted. But this one, presumably, does it have a data sheet actually? Wait, does it say anything about it? Where even is the... Wait, this is so random. Does it say literally anything at all about this thing? But they made a video for it? Why does it look like such a... Yeah, I feel like when you touch something to another like two conductors together, what the yeah. Yeah, when you touch two conductors together, I mean, it really is surface area. Is it hard to get high current through like connectors that aren't bonded with metal together? So they're basically just like pressed on. So like sockets, for instance. What are the variables? I think it... Yeah, contact resistance. Press fit or socket connections inherently have higher contact resistance compared to soldered joints. Gold has low contact resistance. The contact area. The total surface area where the connector and the pin make contact determines how well current can flow. Yeah, how can you calculate? Because when you run current through a wire, it turns to heat because it has resistance. So yeah, so okay. Would Fusion allow me to do a basic simulation where running basically too high a current through a trace results in like a bunch of heat? And I could see that in the simulation. Wait, what thermal simulations does it do then? Like like expansion and wait, so then what thermal simulations does it do? Is it just like expansion and contraction or do I don't know. Probably. If you manually define heat sources. That's kind of wild. Okay, here's what I can do. LTM. Oh, SolidWorks. Okay, wait. Let's look at open EMS heat. We have a heat thing. I feel like it's just yeah. Oh. Uh. uh. What makes doing these like electrothermal simulations tough? Because if there's like if you know okay, for let's just say that there is basically okay, contact may be harder, but let's just say you have a description of basically all of the contacts and all of the wires, but specifically their geometry. So you know the cross-sectional area or I don't know, basically what defines how much current and how much resistance there is across each part of it. And then since you know the material, you know how much heat is generated for a given current, right? So then isn't it just solving the heat equation? Basically being a like bounded by most people can't do like high fidelity uh, PDEs on their laptop. But other than that, it's like not that I don't know. Ohm's law and Joule heating. However, there are several factors that make these simulations complex and challenging, especially at high fidelity. Coupling between electrical and thermal domains. In electrothermal simulations, the electrical and thermal domains are coupled. Yeah, dude, nothing's ever unsynchronized, bro. The world just synchronized. High currents generate heat due to resistive losses. Dude, it's so funny how everything's connected like that. That's crazy. Obviously, that's what happens. If you just think about what's really going on in the wire. High currents generate heat due to resistive losses, Joule heating, which in turn increases the resistance of conductors, further affecting current distribution. The feedback loop makes it necessary to solve these equations iteratively. Dude, I do want to do more modeling, man. I love modeling. I never got good at it, though. And there was never like a... I mean, we just didn't have a good multi-body GUI. Like, gosh. But now there is. I wonder if I could try it. I mean, it is probably... Well, I don't know. In some ways, you got to write code. So might as well just write the code. As temperature changes, the material... Dude, it's so crazy. It's so crazy that their branding right now is... Yeah. Whatever. Okay. So what I want to do... I don't know if I could do this in KiCad or in something else. But the simplest thing would just be literally... I mean, because there's only a few, like, there's only a few geometries that you would need to get, like, most cases. Like, okay. So I don't know how to do the meshing, but I feel like I could generate... Well, I don't even know how I would specify the geometry, really. But, like, I guess I would just pick one to start, and it would just be, like, a rectangle that lies on the... Because that's pretty much what it is. And we just say we know the trace thickness and cross-sectional area. So, okay, so yeah, that... So you would need to know also the substrate. But that's also, like, ambient temperature. Yeah. Can't you just set that... Can't you... You could probably just make the decision that... Which, okay, to start... Because the question that you're trying to answer is just, like, how hot does the trace get? I don't know. You always want the feedback. That's the problem. Is you always want the feedback, but going so high fidelity, it's just you're not gonna get anywhere. So you have to, like, assume that the environment stays constant, and so that you're not actually adding heat to the system, which is, like, obviously not conserving whatever energy, but in this case, I still feel like you'd get an accurate enough stimulation to, like, kind of be able to tell. Because, well, I guess the real question is, when do things break? Like, okay, I guess the real question is, like, when do things break in, yeah, it's really, you want to know at what point do the traces break, because what I was thinking of to respond to environmental factors, like the feedback between, well, like, okay, let's say you were to only model the temperature of the trace, and you ignore the fact that you're actually dissipating heat into the environment, which is causing hotter... What am I trying to say? I'm trying to say when current flows through a wire, there's always some resistance loss, and you can use whatever Joule heating to figure out how much heat is produced. So if you assume the resistance is constant in a, okay, wait, so can I just ask it to like, write some simple description of the differential equations where we just want to know how, basically how much heat is being produced in each part of, basically just a wire that has a constant cross-sectional area and it just goes for some distance. And all we're trying to know is how hot it gets. And yeah. I need some water. Right, because, like, basically, I mean, okay, what does it give you is the question. And what it gives you is the fact that you cannot use this resistor, and you can use this screw terminal if you have the heat, you know. You can know that thing's going to burn, man. It's not going to work. Okay, so what's the point then? So obviously it took super long, but it would also be cool is if, like, let's see, edit symbol. Electric, I don't know. But it would be cool that wait, why isn't the good picture? This picture's so much better. Wait. Okay, whatever. You just look up the data sheet. How hard is that? Okay. So what do we okay, let me just draw it on paper, bro. It's not even that hard. We're just gonna pick. Okay, so I forget, do the ESCs have to be on I squared C? Is that what they do? Or no, you know what I'm thinking of? Oh, yeah, and eventually we're gonna need 4 pins. Oh, and actually, did I ever test whether... No, I think that these are on different I squared C because they don't want name conflicts, right? I'm pretty sure that's what that is. On the Pico, there are, like, I think multiple different I squared C, I don't know what you call them, buses, channels, whatever, because there's like I2C1 and I2C0 I see on the pinout. Is that so that you can, like, have the same, because I have 2 sensors that I think have hard-coded addresses, but that means that they're the same address, so... Whoa. Wait, did you guys see that? What did that say, bro? That was so... Oh, wait. Oh, wow, it shows you the memory now? Dude, that's actually kind of sus. Well, it's not sus, but, like, I tell it a lot of stuff. Let's put it on stream. Okay. Okay, cool. So then, and then 4 pins for the, for magnetic encoders. I can't believe I never did this before. You just actually draw out the electronics of the project. You can wire it together, but in some sense, dude, that's why it's crazy that they don't have a, dude, we need, dude, the Bay Area totally needs I don't know. It's just like, there needs to be a PCB factory that's good, dude. Because it's so nice to have, like, the benefit of miniaturizing all these freaking jumper wires is huge. It's huge. It cannot be understated. It's the same. It's all, yeah. For me, the thing that, like, prevents me from doing any work on a project is, like, it's like, oh, fuck, I need to go grab this thing and work on it. I need to, like, move, like, 10 different things. And it's all like this. And it's just, like, such a mess. So once you just have a PCB, a power supply, it's all over, man. That's why in some sense, actually, we probably should build in. Maybe we can like only use like one, I don't know, dude. For me, doing any layouting or routing work, it's like this is like a hard problem. I don't I don't really want to solve freaking placing and routing. Luckily, the auto routers seem to, for all my simple designs, seem to be able to find a answer pretty quickly. But okay, so all right. So what is the plan now? The plan is to okay. So we have 1 and 0 on this side. So maybe we could just use. Well, we need this, but that's fine. We can go inside. So this could be on the wall of the. Okay, there's actually hello electronics. And then yeah, the electronics part, man, I was not giving it its due. It's actually pretty. Oh, it's actually a lot of work because. Well, you just need to make a bunch of decisions that you didn't have to before. So, um, let's just do this, and I'm just gonna go through and add these labels. Is that N? Is that what I want though? No, it's these. Okay, so let's just go through and add a bunch of these. So those are just no. These are I squared C. I don't know. Do I have to? I probably have to do that. Okay, then. So that's. So wait, which ones are I squared C? Let's just do this. And then we need 3 volts, which is important. But we'll get to that. Okay. So ground. Oops. Then we might as well use these for an. So wait, how many I squared C's? We need. It's the magnetic encoders. So that's. Okay, wait. Why don't we have these be the. Okay, so wait, but you need 4 pins. So this is. I just need some. I mean, I know it's not right, but can you not have conflicts? Okay, and then. Oh wait, you need to add more. Is it N or what? What was it? You can't. Okay, that's weird. I feel like this would be one of the most common things, and you have to go and click for it. Just a little confusing for me. Okay, so now that we have all the magnetic encoders, and I don't know why it's naming it 4, but this is 15, so we can make these the. Okay, so it goes the encoders. Honestly, are the encoders any? Maybe with better software, the encoders could actually do something. Like basic control logic, just like a. The annoying thing though is that you need to have some correction for it doing dumb stuff. Like be aware that it's going to cycle through because. Well, anyways, we'll get to that. I have been putting that off seriously. So the encoders, the. I think the ESCs just take a normal pin. I mean, they're all I squared C, but yeah. Okay, so then let's just do the ground. Oh wait, no. ESCs, steppers, and solenoid or MOSFET. All right, so this is gonna be easy. Do you have to tile the grounds together? They're all tied together internally, so I don't think it matters. So, okay, so these two pins, this is going to be the ESC2. Oh, but the thing about this, though, actually, is, okay, so now I'm starting to get what's going on. So you draw these, like, bounding boxes, right? You draw one of these rectangles, and then you say, like, okay, so let's just do these steppers, for instance. Oh. So then you name this, like, yeah, you name this, like, what are they? They're like dir plus, dir minus, step plus, and step minus. And then you, oh, can you not? Oh, yeah, you can. Yeah, because the only thing you're concerned about here, which you can easily get confused by, is that this is just about getting the schematic down. So, but then what do I want to do? I want to, like, wait, does that make a new rectangle? I mean, I guess you do, but then this could just be smaller. I don't know. I really, the time I did this last year, I was basically just cheating the whole time. It was like not. So then, but what happens if you have two? I mean, is it encouraged to make this like yaw and then just prefix yaw in front of all of them? I mean, does it really matter? And then you do, wait, yeah. Okay, wait, it is for, no, but you know, I'm dumb as hell. I wasn't even thinking about the actual circuit because I don't have it in front of me. These go to the driver. I wonder if we, what happens if we just look up, what is it, A49, what is it? A4988. Does this actually return anything? How do I, can I? You can't copy this? Edit more? Your data sheet? Yeah, it doesn't work on the, yeah, that's why you want to use it online. Oh my god, what is going on? Is it this? Oh shit. What the hell is going on? New project, sheet 1, shift F, and we want to say A4988. Oh, what the hell? Oh yeah, you just can't view it like this. This is not going to work. Now I want to open this thing up. Maybe that just like, because they don't have it? I don't know. View datasheet. How do I even copy any information about this thing? Also, wait, this is like way too many pins. This is not even the right part. I'm actually kind of surprised. Oh, but look at how many. Dude, this is so cool. I mean, that is what it is. That's the pinout. I'm almost positive. I mean, what else would it be? I mean, that is so cool. And I mean, you gotta just realize what this is. Like, how to make a new symbol. I'm pretty sure it's just a matter of drawing these. Like, that's a nicer footprint than that because it's labeled. Huh. Dude, that's so crazy. But this is the, I think that this is the This is the breakout. Oh, okay, yeah. So this is what we want, actually. So we need 2 of these. And then we just, right. And then we just, okay. And then you just make a wire to that. So you still need, so this isn't like wasted work. Like, that is what you got to do. Oh yeah, and I don't think I've ever run this off of power before. But I'm pretty sure if you disconnect it, it just like starts running. Actually, no, because when you like in Rust, you flash it from the start. How does it do that boot cell thing? It like just like the data is probably not overwritten. It's like probably still in there. Maybe not. Maybe little bits of it are, but wait, what was the run pin? I never tested that. Is that as easy as you think? Did some Oh, no way. Bro, whoa. That's fun.
Okay, in this video, we are going to load and run forth on the Raspberry Pi Pico. Now the forth that we are going to run is McCrisp forth by Matthias Koch, who has ported forth to many.
Dude, those stack languages are trippy as hell. I never got it, but I never like, well, I forget how it works. Okay. All right. So, let's just figure this out. Okay, so now we have. Okay, so wait. What did it tell me? It told me to like add the Pico. All right, let's just get all the parts on the page. So this represents these long wires that go to the. But is that how you do it? I don't think you do it with labels. I think you need to add a specific symbol that refers to like a 4-pin thing. Okay, let me just ask GPT. I'm in easyeda, and as part of my schematic, in the thing I'm building on the breadboard, I connect this 1 meter cable that goes to a stepper driver, connects a stepper driver to a stepper motor. What is the proper way to represent the stepper motor in easyeda? No, yeah, actually, this is kind of the pro strat. You should just look up. I mean, I don't think this is going to work, actually. Oh. Yeah, see, oh, that's actually kind of cool. See, this is the pro strategy. You just look at what other. Dude, okay, that's the thing that I got, like, totally caught up by. CAD, this kind of ECAD is actually way simpler than you think. It's all just, like, drawings. It's not, like... There isn't, like, that much going on under the hood that you expect is going on. So what is this? Terminal blocks? Is that the best way to do it? Is just use a ton of terminal blocks? What alternatives do I have to terminal blocks? Is the way to connect... What options do I have to connect this 1 meter cable that... Well, the end of the cable is like a 4-pin, I think, breadboard-like pitch, female, like black housed connector. But then I also have this thing that inverts it, so it's a male to male, or it's a female to male converter. And what options do I have to connecting this to the PCB? I probably talked to GPT so slow, but it's because I'm so dumb. For connecting a 4-pin female breadboard style connector. So if I just look up 4-pin male header. I feel like this search is like not as good as it could be. Like USB 4-pin header. Mainly because there's no 3D. Can we go to KiCad? I feel like KiCad might actually have more 3D. Because the problem is, okay, what they lost when they basically connected. Oh, these are all user contributed. They probably have 3D models. Yeah. See, but it's like a shitty 3D model. I mean, the cool thing is they have the dimensions, I guess. Okay, so what we want is 4-pin. Oh, so let's write this. Yeah, 1x4. See, I don't know. Its search is just kind of goofy. But so that's what it is. Yeah, that's exactly what it is. How do they solder so little, though? So you place this. So this is the... So that's what you do? Wait. Let's look at the PCB. So you save it. We go to project. Wait. Project? What's going on here? Oh. Wait. Oh. And then you go to the Pantel. Oh, wait. No. You know what I want to do? Because I feel like these aren't linked. Because I didn't know how to convert... no, keep going. I like that it does this auto-sized rectangle thing. That's very nice. Okay, so we have the drivers, and these, we could just get our calipers out and verify that this is right. But what does this footprint actually mean? That's the problem. Is like, can we do the 3D? Are those holes? I don't really know what those are. See, they're nothing though, right? Like, so what does that footprint even mean? What does this even mean, dude? Are these holes? I don't even know how to tell if these are holes. Oh, I think we want to be like this. And then the stepper drivers, they just go like, I mean, it literally just goes like this. Dude, it's crazy that I've never ordered a PCB before. Obviously, this is going to be a project where I order a PCB. I don't know what I'm like. Oh, should I do it? Should I not? Obviously, I should just know what it's like. I wonder what delivery is, though. Hopefully it doesn't make me add the billing information first. Let's just make I'm pretty sure this is a valid circuit. And it's a valid PCB. If we, dude, I hate that this is like, close other tabs is nice. That's useful. Wait. Okay. Wait, what happened here? Oh, weird. Okay. Oh, so this is not what I want. This is the one I want. So now how do I buy this? If I just look at the 3D view, it's the stupidest circuit possible. It's literally just a surface mounted resistor. Oh, and a incorrectly rotated terminal screw block. Is this gonna work? Can we just delete all traces? Wait, X. How do you make it? Is it just W? What the hell? And don't you want it like? Don't you want it like this? Okay, so now I save this and then I look at it. Dude, without 3D, it's like sort of worthless. How do you fucking... Okay. No, I think you have them all the way over, actually. I'm pretty sure you actually have them... I'm pretty sure you are supposed to do this. And then see, how great would it be if you had normal CAD stuff where you could just say, all right, put this in the middle. I mean, it's not very useful. That's why it doesn't exist. But like, just for my, it would just be kind of nice to make sure that this is like kind of, okay, fabrication, one-click order, PCB SMT, where they make it for you. Check DRC. Build time 1 to 2 days. Dimensions. One-click order. Wait, but it might open up Chrome. Yeah, so that's what I was worried about. So that's why, okay, that's why I just have to stay on the website version. So hold on, let's just close this. Some changes have not been saved. Like what? Okay, so here's easyeda. Let's refresh this page. Who gives a shit? Okay. Test. Is it new PCB? No, I'm pretty sure it's this. Okay, so fabrication, one-click order. So this is just going to be... So what am I getting here? Wait, do I have two things? Oh, no, yeah. So wait, hold on. Oh, do they give you the parts? Dude, that's so nice. It doesn't tell you who's making this thing. Is that just because, like, it doesn't matter? Wait, select. What? What is going on? Yeah, I'm so confused. Select the quantity? Oh. Wait. Oh. Is it part number? Yeah, I don't really get what that was about. Is this a resistor? Yeah, that's so interesting. So you're not supposed to really use... this. So when we go back to our schematic, we're going to go back and delete this. Because we need to go find, what was that? It's 0603, okay. That's just a size, though. Okay, so what if we just delete this and just go to the library and go to resistors? Do hole resistor. Is there just an, okay. I just want the most basic 0603 resistor in easyeda. What do I search up in the library? If I search for this, am I going to get what I mean, that's a logical. Oh, I'm going to mess that up so much. All right, so we just look at this. Wait, this is an LED array? That's what I'm saying, man. What the heck? Okay, does this just let me... And oh, that's so interesting. Okay, so what this means is that they can make it. Doesn't support SMT. So then why can't I filter by that? Oh, there's value. This is the worst interface, dude. Who the hell made this thing? All right, so... Okay, wait. So we're just in the resistors thing. Wait, can I just look up for 1K? Oh, my God. Okay. The crazy thing is I just don't know, like, is this the best one? It just seems so arbitrary. Is there a cost? They don't even say the cost. Okay. So whatever. We're going to attach these. Okay, now we delete this stupid thing. We save it. And then we go to PCB test new. And we update it. Design import changes. Yeah. Okay. Wait, where the... Oh. Is it connected? I just want to delete them. Oh, is it wire? Yeah, it's wire. Okay. So now we save it. Then we go to one-click order PCB SMT. I'm pretty sure that's what we want. Generate Gerber, one-click order. We want 5 of them. We want green. What did it even say? Dude, do they have the flexible PCBs? I really want to make those stretchy PCBs. They have flexible, but they don't have the stretchy ones. All right, yeah, F44 is perfect. We honestly need 1 layer. Is that cheaper? I'm actually curious. What the heck is going on here? Okay, wait. Calculated price $2. Does it update? It's the same, dude. What if I do 4? So then should you always just get 4? This is so goofy. What does this mean? How many different designs in your file separated by VCuts? As 1. Delivery for single PCB. So this literally costs $2? Dude, when I made my own PCBs, that making one board took like 8 hours, man. I was not happy to get paid freaking $2 for that. That's crazy, man. What the heck? It took me all day to make a freaking board. That's so cool. And how long does it take? Wait, really? 2 to 4 business days? Wait, do they? This is where they build it, right? Wait, but I didn't select where I'm at. Oh, wait, I don't want it to save that, actually. Coupons. Okay, wait. Free, okay, coupon free assembly. No way, dude. They give you free assembly? Dude, this is like getting makers hooked on crack, bro. Oh, you can't get both? Oh, fuck. They're gonna start, for like next 3 days, they're doing like tree trimming. It's gotta be done, but kind of a no. Kind of a nil sound wise, peace of mind wise. It's just gonna keep going. I might move to the garage, honestly. But it's so nice these next few days. It's like the end of summer. I really want to enjoy it while it lasts. Photo confirmation. Wow. Oh wait, what added cost? Is that this? So if I get the stencil. Wait, but oh this okay. Dude, then you might as well just get the assembly. No wait, but this bruh. I'd say this is my first real. This is gonna suck. Dude, the crazy thing about this too is that it's almost easier just to order it and spend the money than even solder it together, which is crazy. Like, cause the correct thing to do is to at least test that it works by soldering it together. But like, if you kind of don't want to do that, maybe just order it. All right, let's go back and start doing the real thing, which is this and this. I think no, I think it's this. Yeah, and I think we can just delete. Wait, yeah, you can just delete this. Okay. All right. So And then, so wait, so don't we just want to make this? So I'm pretty sure we just want to do, so, okay, so let's just copy these. Can we copy these? And we want to just put them right here. No. Do that. Paste them, and they go like that. And then, I'm pretty sure this is what you do. So yeah, so you just put a little square. So if I do this, do I get everything? Can I move it? I can just move it. Okay. So let's just draw the rectangle so that now we are starting to get somewhere with this. Okay, so now the moat. So let's draw another square. And this is going to be the terminal block thing. I don't know how to do this. Wait, is R just rectangle? No. S, obviously. Of course. For square. Okay. Okay. So wait, I need to kind of move. Oops. I kind of need to move. Oh my god. Oh wait. Just deselect it. Okay. Okay, that's good. So let's just do this one. So I actually completely forget what's going on here. Also, I guess today will have to be the day that I finally try micro stepping. We should just do the test because it's really dumb that I haven't. So, okay, so wait, now what we want is this terminal block thing because then we can connect the power to these. And so what is it? Do we search it up here? I'm pretty sure we search it up here. So we do like connectors, screw terminal. Dude, it's like, oh, here, you just have to look for the P. That's it. Wait, did I already do it? No. Yeah. I did in the other one. Okay, so this is tiny. And this is just going to be... Okay. If I have a screw terminal symbol in my schematic, and I want to represent one of the pins as being the like 12 volt, I just connect one of those labels to it, right? And just call it... Oh, wait. Yeah, how do I do it? Dude, I want to like speed this thing up actually. Do you do that? Can I see how let me just go to YouTube and look at someone's schematic.
I had a lot of requests to make an easy EDA tutorial.
Okay, so he does the VCC thing. But then how do you know that it's 12 volts? Because there's going to be two voltages. So let's go to this. So common library. So now this. Is there just a voltage one? I think there is. Net flag plus 5 volts, and you just change. You literally just change it to plus 12, or plus 3 or whatever. Okay, and then we need this. Oh. What the heck? Okay. Yeah, you do need the logic level, actually. So then we're going to need to call this. So then what do? You do this. That seems fine. You take this, you copy this. And then you just place it here. Place it here. I mean, you're just defining the graph. I don't know why I have to trip out so much about it. I guess I just want to ground all the... I mean, it should be tied internally, but... Let's see. I want to see someone... I want to see someone who knows what they're doing. Damn, it's crazy that the noise cancellation filter is not getting any of this. Look at this. They're churning a bunch of wood. You probably can't even hear it, but yeah, yeah, filters. It's so good. Okay, I guess I'm gonna go get it. Okay. I actually don't remember. It's so sick that Amazon lets you browse without logging in. It actually makes it way more open than Instagram and Twitter. It's kind of insane. Is this the whole PCB? Actually, no. Oh wait, I want that picture. Is that the same? Is that the same as this? Oh my god, it's so bad. Okay. So wait, so we gotta flip this around. Okay, wait. Dir, step, sleep, reset, enable. Okay, we have to assume that. Wait, let's just make sure that. Yeah. So this is the same as what I have. Okay, so what do you tie reset to? Wait, so let me get oriented then. Wait, can I see? Okay, wait. So dir and ground are right there, right? Wait, dir. Oh, wait. Oh, wait. These are the. Yeah, so we do need 4 digital pins for the stepper because, yeah, each of them needs a step and a dir pin. I totally forgot. Those go to the computer. Yeah. Oh, I'm so dumb. I mean, it's crazy how hard. I mean, it's literally just you just describe a graph, and it's ends up just being so annoying. But so the way to do this is just do a label. I mean, mainly I'm just not good at it, but it's and you just do this, and you say this is gonna be tilt step, right? And this is going to be tilt der, not that hard. And then this is going to be yaw step, yaw der. And then you just come over here, take these two, copy them, put them here. Take these two, copy them, and put them here. Okay, then, yeah, these only need 2 pins, but you do need to ground them, right? So the ESC, so what you want to do for the ESC, wait, we can full screen this again. The ESC is just, how do we want to do it? Because I think the ESC, no, I'm pretty sure the ESCs are female. So what we want to do is just this same, not that, but we want to do a Shift F, and then we want to look for, okay, so what do you do? Is it just connector? Anyways, I think it's just like 1x2 O2 header or something, male header. I don't know why it's so. So this is female. Right. So is that what we should use for? No, yeah. We want the exact same. So wait, actually, just to be like, I don't know, consistent in doing this. Take these, just copy this, and then Shift F, search that again, and then just change it with 2. How's that? Why is it female? And why isn't it doing the highlight? Dude, honestly, I'm still kind of shocked. I mean, like, this is not, oh, you know what, is it? I mean, yeah, man, this is, I mean, it just, I guess that not that many people use this thing. I mean, you just want to be able to text search in this. Where's 1x2? Oh, wait. No, male 1x20, male 1x2. I'm dumb. Okay. Place this thing. Wait, 2 point. Oh, maybe that is different. Okay, so then this is going to be an ESC. So we just need, yeah. And then we just need the other pin to go to ground. So let's just copy the ground. Wait, so let's, yeah, let's just do this. Copy ground. Because the third pin, oh, wait, no, but we need to actually match the package, right? I'm pretty sure. Let me go look at the ESCs. Oh, actually, I'm pretty sure what we want to do. Well, okay. Let's see. How do we want to do this? So this is the ESC. And yeah, if you connect it on here just like so I bought these extenders, So they're like the female side of this, or the male. I don't really know. Oh, the female side. And the thing is, this is the problem that I had at the time was that I had no way to plug this ESC into the breadboard. But then now I think it's more about length, because if we look at, well, let's see. So, I mean, this is it with everything taken off. And this is the other side. So, it's kind of a janky setup. So I don't know. Extending the length of this is a little bit janky. But the question is, well, for tilt, I mean, that's the thing. That's why we can't even order this PCB today, really, is because tilt is not designed. Yeah. So we'll probably have to hop into CAD. Okay. But I still want to get this done because then I can go solder it, but I have like an actual layout. Yeah, so okay. So the goal of this is really just to lay it out. But we kind of do need to decide whether or not to extend the length of this thing. Okay, so right now the assumption is that the PCB is just like dangles behind the bolted in thing, which is pretty boneheaded. But I feel like we should just do it. So in that case, okay, wait, what are they called? XT60 or something? So can we just look that up in this? Oh, yeah. Oh, so that's sick. And you can buy them. So they just go into the PCB. That's so nice. That was nicer than adding a resistor. Okay, so which one do we want? We need, well, actually, yeah, how do we want to do this? Because the other side of this, oh wait, but this is only because I had stranded core, I think. These went straight to the power supply. Right, so the question is actually, what does that need to go to? So what is this? This is the ESC. Yeah, so what we actually want is a male. Oh, wait, we can't just change this. Oh my gosh. So it's undo. So, we actually want is, great. Yes. The exact opposite of the part that I would like to. I mean, how does that even... I'm so confused. I mean, the main thing is I guess they maybe don't have I feel like they would have sales information of which of these parts is getting the most and then just sort by that because this is goofy as hell. So wait, let's just look at header 1x3. And it's just like totally different parts. I don't get it. That's what we want. That's what we want. Right? Wait. How come I can't? Oh yeah. So it's short on this side. Okay. And you do it from the bottom? I guess it sinks in because it's plated on the inside of the through holes. So that's what we want for. Okay, that's what we want for the ESCs. So this is like, so can we just add a text thing? So this is like the to ESC computer, or like it's like the other thing. And this so what we want here, and what order is it in? It's gonna be ground on the bottom. I don't know if that's standard. So this is grounded, and then you have the 5 volts. But is there a Q? Can I do a Q? How do I do a disconnect? No connect flag. So we're not gonna do anything with that. And then a what's up with this? This is a and I'm pretty sure that this is how I burned out my, because I forget what. I don't know what I did. And then this is the signal. So this is going to go to, so that's ESC1. So that's what we want to copy is here. This is just ESC. And then you can just take this whole thing and then just change it to ESC2. And that's it. So wait, can we just, can we save this and then go in here and then, what is it, Alt-I? Alt-I. I don't know why they... Okay. We probably are going to need to eventually, when we order this thing, once a lot of other stuff is working. So see, this pitch is actually... Okay, yeah, but so... Wait, shouldn't I have 2 of these? Oh, I do have 2 of these. Okay, so... We have this. All right, so let's just do that. And then power. Let's just put power. What is it? Is it like that? I can't even tell what this means. No, it's not. It's like this. Oh, do we want to do it like that? What is this? Oh, this is that. That's fine. Okay, so now let's maybe like that. Okay, now route, auto route. Obviously, I'm auto routing. I mean, that's it. That's so easy. It's not done, but like... Wait a minute. These headers... Wait, we have that. What do these headers even go to? Oh, right. Wait, so actually what we want is like that and like that. Is that right? Or do we want to flip this thing around? Wait, is this net even right? How do I just delete unroute all? Nice. Oh yeah, that's perfect. And this is, okay, wait. So let's save this and then look at it in 3D. Okay, nice. I mean, this is such a stupid board. Yeah, man. The other boards we had like tons of different and then one of those steppers is just unused. Wait, what are these 3 pins here? No, this is to the ESC. So wait, okay, so now we need to add the other like so we need a so we want to group these together. That makes the most sense. So wait, so let me just undo the copy. We're just going to take all of this and move it here and make it bigger. Okay, so what is the other thing that it needs? It needs I mean it's so hard to visualize what it's actually going to be because like the end of this is just like stranded copper wire. So but I feel like that's like a terrible way to do things. Like we don't just want stranded copper wire soldered into the board, right? We want connectors. Dude, this is like part of CAD where you like isn't really covered by I don't know. At least I haven't really seen that many people where they actually cover like the wires themselves. Do people model wires in CAD? I don't know. Okay, so let me just ask ChatGPT. Okay, I'm trying to figure out how to attach my electronic speed controller for the flywheel of my Nerf shooter to the PCB I'm designing. So the part that goes to the motor is just the 3-phase, so just 3 wires. Then on the other side, there's like a 2.54 pitch 3-pin female connector, and that's for ground voltage and signal for the controller to go to the controller, and then the power, it comes from a male XT60 connector, and basically I don't know what the recommended way, because the thing is, I think I'm going to have the PCB a little bit far away from the flywheel, so I need to extend the distance, but then I just don't know what connectors to use, because right now I have a female XT60 side, and I just soldered some like relatively high gauge stranded copper wire to it, but it seems like a hack to just like put stranded copper wire into the PCB and manually solder it like that. I'm sure there's a better way. Oh yeah, I could just add another screw terminal block. Yeah, I really have to decide how long this thing is going to be. Yeah, because this all comes back to what setup is going to be like, what assembly is going to be like. And so this is sort of the procedure. Because the great thing about drones is that, I mean, these ESCs are very optimized for the drone form factor. I mean, it's not like it would be that much different. Like, this length is pretty good for me, too. Dude, we should definitely... I don't know how to do this, but, like, it would be very cool to do, like, a thrust thing. Because I have these motors. I might as well, like, put a propeller on it. But I don't know how to measure that. Okay, so I'm kind of happy with... But, okay, if we're going to do screw terminals on the end of just added on wire, so you take these, whatever, extenders, and you just have to build that, and you document that. Then you need an extension for this, and presumably it's about the same length, because these are both going to the PCB. And then what you would do is you would leave on the XT60, or you'd probably leave the extenders. So it's not going to be in the schematic because it's not related to the PCB, but basically we need to find like a 3-pin male to male. Wait, do we want male to male or do we want male to female? Should I have like male headers or female headers on my PCB? Is there a... I mean, but I feel like then I want the male. So then I want this to have male and then a female on the end. Okay, so it's funny because that's not even part of the schematic, but it is. So it's going to be like the ESC has the XT60, which goes to another XT60, which goes to stranded copper wire. And then that goes to a screw terminal. Okay, then you have the 1x3 female to 1x3 to connector to wire to then 1x3. So this is going to be male, and then this is going to be female, and then this part is sort of the PCB. This is the PCB, and this is going to be 1x3 male. So that's the connection. So all we have to do to add that in, I think, is go over here. And so this is correct. So we're going to do this. And we just, I think no connect is fine there. But so now we need a screw terminal with 2. So we just need to copy this thing. And then this is going to be just the same thing. Oh, oops. Actually, could we just do this? Okay, and then I think that's it. And we can take this and copy it. Let's make this ESC2 and then make this ESC2. Okay. So now so these are screw terminals. Okay. so let's go to this Alt I. Does it like is it gonna like replace everything? Is it gonna like do the whole world? Oh, wait, that's nice that it swapped me over and it's like you didn't change anything, bozo. Okay, so now we have these, and these go to the ESC, and maybe we want to put them down here. What does this go to again? I thought I had 2 of those. Wait, what's up with the... Okay. What does this go to, this 3-pin thing? I mean, we haven't even modeled the solenoid and the MOSFET yet, so... What is H3? It's hard to figure out these names. Oh, wait. No, H3, where's H4? Oh, here's H4, okay. So the real question is, okay. So maybe like that. I don't know if this is just like dumb. So yeah, this, it doesn't really matter where we put it. Oh wait, yeah. Oh wait, I think you want it, no, I think you want it all the way in. Okay, so if I save this and then look at the 3D view, does it update? Okay, great. Oh wait, we did do it the wrong way. Wait, we did both of them the wrong way. Oh wait, the arrow, bro. I'm so silly. This guy does not know what's going on. This guy does not know what's going on. Okay, so now we have this. And we need to we need to change the footprint for the Pico because that's not what we're going to be using. I think you can though. I think you like because I bought initially a couple of like Picos, like a Pico W without headers, and I think maybe you can just solder that directly to a pad. Dude, I wonder what they use to like simulate whether or not the parts are gonna like fly off of it. Like if it's because like for real, like for a Mars rover or like stuff that's like going under like just super high reliability, you probably want to know just if it vibrates a lot, how much force it takes to like. I mean, maybe it's just not even a concern, but like if a part just flies off of the, maybe something that's more lever-like, something like one of these screw terminals. Anyways, let's, how do you update it? File, what is this? It's kind of weird that their text is like that. I guess you just have to manually do that. Is this fixed now? No. You have to close it. I saved it, but then you click on this. All right, there we go. I mean, they say they're rated for 10 amps, so we're good. This is kind of awkward. I wish it had like, dude, I wish auto layouting was a thing. I guess everyone does. Because it just looks so ugly, bro. It just does not look good. Okay, so let's just add what's the next? So we have so these are the stepper motors. Okay, can we auto route this thing now? What is this? Oh, it has okay. That's fine. Dude, with 2 layers, you can just do anything. I mean, that's not true. So okay. So what's next? We need the MOSFET and solenoid. We need the correct the A4988 pinouts. What else do we need out of this circuit? I think that's it, right? Do we have the magnetic encoders? These are the no. These go to the stepper. These go to these go to the ESC. So we need the magnetic encoders. So the magnetic encoders also will probably just be normal pin headers. And we need to make sure all these wires are the same length because it's all going basically to the same place. I've sort of given up at the moment of doing full 360 because I don't know. You look at I got a slip ring, but the slip ring only handles 2 amps, and it's just like, all right, let's just get something that shoots like a normal field of view. Well, and then I guess we have to actually fix the CAD to do the magnetic encoders thing. And then we need to write the code that actually does that. Because at the time I did a day where I was just like doing a couple trying to sample basically how fast the encoder is going. And it was kind of accurate, but it was only accurate at really low throttle percentages. Okay, so let's just do that. How many pins does that use actually? I think they each use 4. I bet someone has the footprints for this part though. It's probably in my GitHub. Let's see. Bomb. It's probably not bomb. It's probably part docs. Stepper driver pinout, BLDC, ESC. Well, what we need is the magnetic encoder. Where's the? We should make this all one thing, but it's whatever. Let's just look again. It was like that AS something. Yeah, this. I like that it comes with the magnet. That is really good. Okay, so this is what we want. So now we go to back to easyeda. We go back to this, and now we have 2 of these things. So now we need to look this part up. So that's the chip, right? Or is that the that's the chip, which is great. But what we want is the breakout. I think that might be it. Dude, it's so okay, I gotta clean up these tabs. Okay. So I mean that looks exactly right. But okay, but the thing is we're not actually putting that on the So what is its footprint though? Because you need to, or maybe you don't, but So we just need 2 data pins. So what are the? Oh, it's gonna be SC. Yeah. So it's gonna be called like ENC1, SCL, and then ENC, 2 SDA. So okay. So we need a 4-pin male thing, I guess. The thing is, where do we get these? I mean, online they sell like, those standard 2.54 millimeter pitched female and male connectors of various sizes. But the thing is, what do I do if I want my own with that has a specific length and maybe even like because I basically need a specially length jumper type cable, but that like has uh like a 1x3 female or something like that. They're called DuPont connectors. Oh. Not the best rating, but honestly though, this might be kind of the move. The thing is, it's specific to this, but I feel like if you're gonna get 28 to 18, that'll be good. So can I see this DuPont crimping? Yeah, dude, this is what I want to watch.
Making your own connections allows you to make wires of any length that you require with any combination of terminators as and when you need them. Mini PV, better known as DuPont, are common in hobby electronics. They're the style of connectors that you'll often find on the end of the rainbow-coloured jumper wires. You'll need just a few things to add these super simple connectors to the ends of your wires. Some plastic DuPont housings, and some DuPont connectors, and a crimping tool. To make my connectors, I'm using this simple low-cost kit. You'll find a link to it on Amazon in the description below. First, you'll need to choose between a male and female connector.
I feel like this might be a good buy.
You'll want one of these metal connectors. They often come on a roll and can be easily removed by bending back and forth a few times. This is the one used for the female connections, and this is the male type. They both share some similar features.
Hopefully you only have to do it like...
This open V end will hold onto the insulation of our wire once crimped. The open U-shaped section will make contact with the core of the wire, and then the remainder of the part makes up the physical connection between your wire and the devices that you're wanting to connect to. Once you've chosen your connector, you can place it into our crimpers. Our crimpers have several different sized recesses for the different sized connectors. You can also remove this screw, turn the cog, and reinsert the screw to change the strength of the crimp. This lever here allows you to release them without having to complete the crimping action. Just pull the lever upwards, like this. We start the crimping by seating the connector in the jaws of the crimper itself. The V-shaped piece should be facing upwards and pulled back so that it stops against this ridge. You can then partially close the crimpers to hold it in place. Strip about 5 to 7 millimeters of insulation from your wire and then insert it into the connector. Check on the other side of the connector that the wire has gone inside
this
the tunnel
sounds like
section before
such a
crimping.
pain in the ass.
If I show you about the crimper in the way, the positioning should look like this. If all looks good, squeeze down on the crimpers to make the first crimp. I like to then remove the connection and repeat the crimp on the next size down to ensure a good crimp is achieved. Check the connection for these 3 things before proceeding. Is the insulation gripped by the V section? Is the U-shaped section now gripping the wire conductor itself?
Dude, there's nothing. I feel like there's nothing more frustrating than these loose crimps that you just know are gonna fall apart.
Still inside the connector. If all of this is satisfied, then we can choose the plastic housing. Your choice will be defined by how many wires you would like to group together in one connector and what layout you would like, such as in 1 row or 2.
So how does the female work?
The male or the female part of the metal connector. They both use the same plastic housings, and they're both inserted from the wider end of the housing. When inserting the connector, ensure that the open top of the connector, where you can see your wire, is inserted facing upwards so that this ridge engages with this tongue on the plastic housing, which will prevent the connector from being pulled back out of the housing unintentionally. The male connector is done in much the same way. Seat the connector in the crimper, strip the wire, insert into crimper, check positioning of the crimp the wire.
Because what are we connecting here? We're connecting the encoders. So yeah, I feel like I'm gonna make this buy. So what is it called? What did I look up? DuPont. I mean, it just seems like a, if you're in a bind and you just need a wire of a specific length and you need to connect it to something, I mean, it's just such a pain to deal with the wires. And I don't know if the holder, if the thing that you put it into, this thing, I don't know if it handles like any size, but this honestly seems like just a nice thing to have. Bro, I feel like this is going to be a banger
of a bad electrical connection, which in the worst case can create a lot of heat and eventually even start a fire, which almost happened at my parents' house 2 years ago. And no, I didn't do the electrical wiring there that caused this problem, but I repaired it afterwards so that something like this will not happen again. Needless to say, having good electrical connections in your house wiring or similar is key when it comes to safety, which I always pay attention to. But on the other hand, I sometimes do some very sketchy stuff when it comes to the electrical connections of my perf board projects. And thus, I started to wonder what would be the best electrical connector you could use. So I got myself all the common ones, like Vago terminals, screw terminals, all kinds of cable shoes, and of course ferrules, which are super important. And in this video, I will conduct a rather big experiment in order to not only find out what the best electrical connector type is, but also to show you how to use each one properly. Let's get started.
Dude, this seems like a banger.
This video is sponsored by Knipex, who provided the two crimping tools that I will be using during the video. First off, what is wrong with the way I connected a copper wire to my project through a PCB screw terminal? Well, the problem is not the terminal itself, but instead the used wire type, which is stranded wire. As you can see, it consists of very thin individual conductors, which come together to form a bigger conductor.
But I would think that because solid core, well, let me hear.
This way, the wire is very flexible, which is great for non-stationary projects. On the other hand, of course, you got solid wire, which only consists of one big copper conductor, and thus it is more stiff. Now, using solid wire with the screw terminal is completely fine, and can often be seen in your modern house wiring. The reason is that as soon as you apply pressure with the screw, the big copper conductor holds against and thus is kept under pressure properly for a long time to come. But if you try to do the same thing with stranded wire, then you might have a good connection at first, but eventually the thin copper wires will give in and lose pressure. Which brings us to the big problem of electrical connectors: contact resistance. You see
man.
now that there's less pressure
Dude, it's crazy, bro.
the
Yeah.
thin wires in the screw terminal, there's no longer such a good electrical conductivity. There's less pressure between the thin wires in the screw terminal, there's no longer such a good electrical conductivity between them, and thus the so-called contact resistance increases. Since we know that resistance equals voltage divided by current and power equals current multiplied by voltage, we can come up with this formula that states that the power loss equals resistance multiplied by current squared. So if, for example, the contact resistance doubles, the generated power loss doubles as well, which, by the way, gets dissipated as heat. With more heat, the electrical connector can potentially warp, and thus increase the contact resistance even more. This can become a vicious cycle, in which not only heat gets generated, but also if the stranded wire becomes completely loose, can lead to the creation of tons of sparks and in the worst case to a fire. Needless to say, we want to avoid that, so why not just simply solder the thin wires together to create one big conductor and insert that into the screw terminal? Well, sadly, this is also a no-go, since the soft solder will also lose its applied grip over time and thus enter the vicious cycle from before. A solution to this problem, however, are such wire ferrules, which, with the help of a bit of external pressure, close around the thin wires and thus turn them into one solid conductor. To use them, you simply need to know your wire cross-section, in my case 1.5 square millimeter. Then select the fitting ferrule according to the color scheme, remove 10 millimeter of insert.
Oh, so maybe I should get some high gauge stranded too. I mean, it's not like this needs to, I don't know, maybe having lots of different types of wire does seem useful. Maybe I'll get some high gauge stranded.
Put the ferrite on, place it in the crimping tool, and off you go. And just like that, you got a perfectly screw terminal usable wire. But of course, screw terminals are not the only available option when it comes to making good electrical connections. There are also Vago terminals, cable shoes, simple soldering, and also butt connectors, whose name I didn't make up. Vago 221 terminals are my favorites, and can be used not only with solid wires, but also stranded wires, since it comes with a spring mechanism inside, which constantly applies pressure. Cable shoes, on the other hand, are for more special...
See, I wanted to 3D print that. I really wanted to design and 3D print that, so that I could go around the nibs of the old... DC motors.
Comes with a spring mechanism inside, which constantly applies pressure. Cable shoes, on the other hand, are for more specialized connection tasks, like connecting
Can I
to
look
constant
those up? How do you
wires,
connect this
whose
to a
name I didn't
board?
made up. Vago 221.
Everyone is talking about. Dude, I gotta.
This is the Wago 221 inline connector. So in this video, we're going to take a good hard look at these.
All right.
One terminals are my favorites and can be used not only with solid wires but also stranded wires, since it comes with a spring mechanism inside which constantly applies pressure. Cable shoes, on the other hand, are for more specialized connection tasks, like connecting to a battery or, for example, creating a ground plane for your moped's electrical system. To use them, you simply choose a fitting one according to their color, which once again represents different conductor sizes. Strip around 7mm of your wire's insulation, put the shoe on, and use the correctly colored segment of your crimping tool in order to bond the wire with metal through pressure. And last but not least, we got the simple solder connection, which can be done by simply soldering two wires together. Only problem about that is that in comparison to the other connectors so far, you cannot easily separate the conductors from one another once the connection is done. The same problem applies to the butt connectors, which, by the way, get crimped to the wires in pretty much the same way as the cable shoes. And now that we're familiar with pretty much all the common connector types, except maybe the JST connectors, which I sometimes like to use when I got lots of data lines and only left out because you usually do not draw much current with them, which one is the best one? And with best one, I mean the one with the lowest contact resistance. To find that out, I got my highly professional test equipment here, which I will hook up to all the different connector types according to this schematic. Now the power supply will pump a constant 5A or 10A into the circuit, which I will confirm with my multimeter. And all I have to do is to measure the voltage drop as close as possible to the connector, so that the majority of the voltage drop will be from the contact resistance instead of the wire resistance.
About that. Yeah.
Then all we have to do is to divide the measured voltage by the current, and we got our resistance. And with the explanation out of the way, I started the experiment, which pretty much had me curious all the way through, because I actually had no idea which connector/connection would be the best. Except maybe the solder connection, since there we are basically fusing two metals together with the help of another metal. Now, taking all the measurements took me around 3 hours in total, because I actually used 3 different wire pairs and also 3 connectors of the same type for each measurement,
what a baller.
so that I can later calculate
a
reliable average value. And after I finished up my note sheets, I moved all the measurements into the spreadsheets.
Hell yeah.
I was pleased to see that the measurement difference between wire pairs and the same connectors was very
little.
That's
great. Dude, this video is so good.
Connectors do a very reliable job every time. Into the spreadsheets. I was pleased to see that the measurement difference between wire pairs and the same connectors was very little, which means that the crimping tools and connectors do a very reliable job every time. Also, the calculated milliohm value for the 5A and 10A measurements were also very close to one another, which means that the connectors do not mind a higher current flow, but always make sure to not exceed the manufacturer's given limits. And now, let's finally get to this chart, which clearly shows us that the winner of this resistance contest is the solder connection, followed by the butt connector, cable shoe ring, screw terminal, and then Vago terminal. The 2 worst performing connectors were the cable shoe push-on, which was obvious due to its wiggle room, and the PCB screw terminal, which was quite a big
What is that in milliohms?
push-on, which was obvious due to its wiggle room, and the PCB screw terminal, which was quite a big shock for me since I love using them. But keep calm, because with the average resistance of around 2.2 milliohm, they create a power loss of 0.22 watts at 10 amps, which is certainly a bit riskier, but seriously, when are you going to draw 10 amps through them?
Wait, but I am gonna draw 10 amps through them. Or at least one of them is gonna have 10 amps go through it. That's crazy to think about, dude. I mean, I'm gonna be drawing like 13 amps through them, hopefully, because 8 amps for the solenoid, which is crazy to me that it just takes so much current to do that. And then I think 5 amps for both drone motors. So 13. Dude, what a good video. He just makes such good content. Okay, so where are we at with this? Oh, I never added this to the whatever, it's fine. Oh wait, yeah. I think it is this one. Oh my god. Okay, so let's go back and let's just finish this thing up. This is right. This is definitely what it is. So, but what are we representing these as? Because they're not going to be on the PCB. So what is their footprint? Like if we were to just save this and then just so in the 3D view, what does it look like? Oh wait. I forgot you have to like, because we're not mounting them to the PCB. Right. So yeah, so we're not doing that. We're doing the inverse of that. Oh, and we probably should add mounting holes. Let's see. Okay. The other thing is we need to yeah, power for the Pico. Luckily yeah, it doesn't have the 3D model, but well, and we need a power Pico and fixed footprint. So that should just be like well, if we could probably look for Pico footprints that are exactly what I'm talking about. So what happens if we go back and search up Pico? Wait, hold on. Wait, can I just add this in? Is this what I did? No. This one doesn't seem to have the USB. But let's save this, and I just want to look at... Okay, let's just move these. Okay, so this may be closer to what I want. Right, see, that's what I want. Okay, so that's the... Okay, oh, wow. Wow, dude. Wow, dude. Yeah, so that's what we want. Because... Wait, is it, though? Because I just want the holes. I mean, in the PCB, these are just holes, right? What is this? It's a hole. Okay. Okay, let's just finish this thing. This is so boring. Wait, but I'm trying to figure out if this is really what I want to do. Like, no. What I need to put in here, okay, so let's see. How do I make a custom footprint? I'll just make my own and try to copy the pins or whatever. Or actually, no. So wait, hold on. Let's see how to do this. Footprint. Select footprint. How do I make a new footprint? I wish there was like a command palette. There we go. Okay, so we just need to measure. How do we measure? It'd honestly be, wait. It'd honestly be easier to like, can I measure? There is a measurement thing for sure. I just don't know what it is. That looks like it. All right, 17.7. Okay. Okay. So this is all we need to do is we need to place a wait okay, so we just need to do it by holes and all that. It's like a yeah. So wait, but this isn't gonna be a hole. I want to use an existing footprint. Can I use an existing footprint? Probably, right? Is it 20? No, it's like 15, right? Wait. I don't know if that was the same. Oh, it's 6. Wait, how do we get 40? Oh, wait, there is 20. Why did yeah, I was looking at the wrong thing. Yeah, so it's 1 by 20. That's what I thought. So you can go here, search for this. There we go. Yeah. So now we just place that. Oh, wait. So wait. We can't. Okay, wait. Let's just try to go to this. Do new symbol. Is it found new symbol? And then we're just going to copy a bunch of stuff, right? Right, because what this is this has this silk screen thing, right? Oh, wait. Oops. How do you do layer views? I think. Oh, that's backup. We don't want that. I think they're. Oh wait, this is it. I was not looking. Wow, is that bad UI, dude? What the hell is that? Okay, so let's just look at. Wait, let's just look at. This is the silk layer. Right. So we could keep that. We could keep that. Okay, so wait, what is the footprint for these is literally just a hole, but then the 3D model. So we would need to make our own 3D model. Can you even do that? Oh yeah, you can. But you need to make it somewhere else. Interesting. But am I doing the soldering or not? That is kind of the question. I mean, either way, it really doesn't matter. But yeah, so in the end of the day, it's just holes. So that I think that this is right. I think that this is all we need to use. So we can just replace this with that. So it's not like the easiest thing to do. I mean, it's not like because these are, well, let's find out. So we're going to delete this. Wait, hold on. This goes to 9. So we're going to delete that. We're going to take this and make 9. All right, nice. So we can save that, and then we can import the changes, or Alt-I. Okay, and then those need to go. So then this is like this. And so the 3D model doesn't look like what it's going to. Because this is going to be raised up a little bit. So this is actually going to be... I wonder if we could make a new 3D model. Because the thing is, this thing doesn't have headers, so I don't really get what this is. So these also will need IC holders, but the question is, the stepper motors actually draw like very little current, so I'm not really worried about that. They do get warm, but I think at most they draw like an amp, so like most just like generic ones of these can handle it. Okay, but the annoying thing about this is I'm doing this and it's kind of fun, but like I'm realizing now this is not really what the strip board is gonna look like. Well, is there like just a strip board or not strip board? Is there just like a perf board editor? Isn't there a scripting? I think I saw someone actually order. I'm pretty sure a long time ago I saw someone just make perf board on KiCad and then just order it from PCBWay or JLC. I don't really want to make one, but but we do. Okay. Here's the thing. We do want to mount the Pico onto the perf board. All right, so it's time to start doing this because I need a solder because it's already 3, dude. I gotta go to class at 6. So let's keep this thing pushing. So so this is still useful. Is it? Is this even useful? Dude, this circuit is like way more complicated than you actually think it is. All right, so let's add. I hate this U3, U4 thing. Why not just put what, if you have the space, just put what it actually is. This one got overlaid. I don't even, okay, yeah. Okay, what's next? What's next is let's just do the MOSFET. And what was the type of MOSFET that I need to use? I don't even remember. I'm controlling an 8 amp solenoid with a MOSFET, but I don't know which type to use, and I'm going to be controlling it with a Raspberry Pi Pico. I also don't remember the diode type, but I think it was those 1N504s or something. But it was weird because it says like yeah, I didn't understand. This came up like recently, but I did not get it. Yeah, this sounds right. So now we just want to go into here and like add it, right? That's all we have to do. I mean, I want to know what package it's in, but yeah, it's okay. So presumably it has to do with the package. So that's through hole. Oh, and this is the. Wait, can I, dude? I'm so sick of this thing being so small. Okay, that is just ridiculous. Oh, I love the costs down here. That's so cool. Oh, are they sorting by cost? So now we need a FET here. Okay, we need a. So wait, what is this? We need to add text to all of this. Okay, this is. Two stepper, two yaw stepper, two tilt stepper. Yaw driver, tilt driver. This is can I type T? Oh, but it doesn't. Okay, two power supply, or I could just write power supply, and then we can just write two ESC because it goes. Okay, then what do we have to do with this actually? Oh wait, but did we? Yeah, so we probably have to redo this because I don't think we. Oh no, actually we're good. We're good. I squared C 0 and I squared C 1, so we're like, big chillin'. So let me. Well, actually, let me delete this and then draw a square. Okay, so. Well, I don't remember what this out is. I think that's a no connect. I don't think I used that. But then this and this. What the hell? Okay. Do we need all four? No, we just need DIR and SCL. No, we just need SCL and SDA. Right? I'm pretty sure. Okay. So we just add a label for it. Is it this one? No, it's this. This is gonna be or wait, what the hell? So wait, we need to be that. Which one was that? I should have made a note. 6 and 7. Why are these different colored though? Just because but they should be fine. I mean, it says it, so we're good. So then we just want to use the 2 above it too. Dude, why is it doing that? Okay. Oh wait, we can just, okay, we'll do this, then we'll do this. But the thing is, these footprints, oh, wait, so how do we want to do this? We need to have, because they're, I can't remember what I use. Yeah, I just broke it off the table. I just broke it because it's like, when am I going to need this? So, yeah, so both of these were done just directly wired in. But so that means that on this side, we actually just want like a 1x4. But the thing is, we want to know, does it do that little thing with the square? Because I think ground is usually like square. Is this grounded? It doesn't mean that that's ground. It means that it's pin 1. So is there a standard? I've noticed in ECAD that the first pin, or some specific pins, I don't actually know if it's pin 1, is like square in the PCB design as opposed to like a circle. What is the significance, and is there a convention to like make pin 1 ground because of it or something? But maybe that's the right way to do it. Because I feel like I'm always going to forget. Also, this wire might be too thick. I mean, this thing needs, like, nothing. So to have something this thick is kind of silly. Maybe I could get some... I don't think you can use stranded wire with those crimping. I don't think he said that in the video, but I don't think you can. So, what does that even mean? So wait, so when we go to this, display footprint, unknown, where do I select edit symbol? It's crazy how little this is, I mean, that's nice. How do I change the footprint? Oh, wait. Oops. Oh, yeah, okay. So wait, can we just... Is this the footprint? Oh, these are all my footprints? Oh, okay, okay. How do I edit the footprint? Do I have to... Oh, I have to make it and then I have to search for it? Okay, what the heck? There's got to be a way. Can't I just take the 1x4s? Because this is literally what it's gonna be. Edit symbol, footprint. Just take this footprint name. Do this thing. Search for this. I don't know which one. VM. This one, I guess. And then let's see here. So wait. VCC is 1. Nope. Wait. So wait. I don't know what that means, but ground, yeah, dir, we don't need in this. So this is gonna be 1, 2, 3, 4. And so there we go. So now, but that's not gonna be this one either. So wait, I wanna just do this and delete it. And watch it move the thing. I don't know what that's about. Okay, so now we should be able to save this, go in here, design, import the changes. Wait, hold on. Can we go back to this thing? The pad number. Wait, what happened? Oh, I thought I saved this thing. Wait, dir What is GPO? Dir, GPO, and out are not used. Didn't I say that? So this is 1, 2, 3, 4. And this fails or something? Is it still red? Can you just delete them? I don't think you can delete them. But yeah, but this is what we want. Is we want a female connect. The male is on the PCB, and you just plug it in. So then what? Okay, so then it doesn't let you do this because you have to have right because it just auto assign them to something random. Wait, what if we just change this to 4? It's red still, but like, wait, actually, this one didn't even take my change. If I do update footprint, I'm pretty sure if I go like this, it's just gonna, yeah, it just resets it. So I think the best thing to do actually is you don't even do this. You just do this. Or take this. And you yeah, you just say and then you say yeah, then you just copy these two. Yeah, I think that's it. Oops. And you just copy this, paste it, and then you delete these two. And then you take these two, copy them. Is that connected? I can't even tell. Okay, so now we should be totally fine. Okay. So see now, wait, what is this? Yeah, okay, right. What does this even get me? I mean, it gets me away from a breadboard, but I'm trying to figure out what the perf board is going to look like. The perf board is going to be kind of brutal. So wait, what are these? So, okay. Yeah, so these just get read from the... I don't know what these X's are. What are these X's? Oh, they're in a keep out or something? I don't know. Are there more X's? I don't see any more X's. Maybe it's only for those... What is this? What the hell is this? This is the yaw step. Can we just... Dude, what? So how do I want this to be? With the arrows, let's do it like this. Like this. Add 3 of them. I don't know. Maybe we should put this one up here. Is it the power one? I'm pretty sure that's the power one. And then what? Dude, these names. Is there any way to see a name for this thing? Wait. Okay. If I click on this whole thing. Maybe there's like a. I don't know. What's going on? What's my G word? My G. Okay. So I feel like the best thing for these though is actually you do something like this, because you can go through, but then so is it this? Take this, and then you just yeah. See that's kind of better. We need to check that that's right, but that seems better. Because this is all stuff that we would maybe want to control. Like, we might want to dynamically, which is actually kind of why. I mean, I don't know who would want to change microstepping modes, but you might want to do it. So now we want to do this. And we need to fix these, but for right now, yeah, okay. And then you move, what is it? Is it this? Why do we have two? The 2 more are for the sensors. So yeah, so those are kind of better to put. When was that? That was a long time ago. Okay. So what is this? This goes to, what is H3? H3 is, oh, the ESCs. Okay. So yeah, so we went the ESCs towards the bottom, I guess. Oops. We got a theme. So this goes to ESC, as does that. So maybe we could do it like this. What are we missing? We're missing, okay. Q1, this is the FET. And, oh, the FET is not even being used yet. What is this? H5. Okay, so this is the magnetic encoder. Yeah, so let's take these. Wait, let's take this, this, and this. Or this. Let me just move it way in. Oh. Lol. That's so annoying. Let's look at the 3D. So these go to the stepper motors. Oh, maybe we want to put all of that on the bottom. Let me go get what I actually have. Okay, so here are the actual perf boards that I have. Thing is, in a way, strip board is easier. And actually, I could just use the I could just use that because I have literally a breadboard. The question is how, like it's like a mix between a breadboard and a perf board. But I don't know what current those things can handle. These are presumably. I don't know. Maybe it's the same. I mean, it probably is the same. So then those perf board, breadboard. I don't know where I got them. Yeah, I guess they're kind of like this. Oh yeah, let's do solderable. I mean, they're gold plated. I don't know if mine are gold plated. Are those tied? Why is that? Does it tie plus together? I can't tell. Okay. No, I want the. That didn't work. Yeah, female header. Yeah, 20 female header. Maybe that'll work. Oh yeah, there you go. Yeah, header strip for Raspberry Pi. The thing is this? Why is it 2 by 20? Do you split? Can you split it in half? Why are they all 2 by 20? Is that 2 by 20? That doesn't look like 2 by 20, but it also doesn't even look like 20. Yeah, I don't know what the hell is up with that. Can I just specifically look up 1 by 20? Yeah, see, this is exactly what you're looking for a breakout. I think we have one of these, but does this have a 20? If it has a 20, it's probably the... Yeah, 1 by 28 pieces. Yeah, let's just look up 2.5. Oh, wait, hold on. No, wait, what am I looking at? Is this a better? Let's see, does this have? Oh, it comes with JST as well. But it has way more ratings. I'm gonna cancel the other one. Okay. But um okay, what the heck am I doing? So I'm getting this too? Or not that, but wait, hold on. I don't think that this one comes with the 20s. That'd be surprising. You don't really need 20s. You just need to line them up. It makes it easier though. And you can always just use one extra. So what does this have? 4, 6, 8. Yeah, so if I want to put in All right, so let's just look at one of these PCBs like this. Okay, so it's just a fuck ton of. They probably just use JLC PCB, man. I mean, the same stuff. Okay, wait, these are all the small ones. Are there bigger ones? I thought there might be bigger ones. Okay, it's not as big as I thought. Okay, so the biggest one is this big, which is like, let's see, it has number, oh no, that's great. That's great. It goes up to X, so what is that? Thing takes so long though. But yeah, we can do dude, I could have figured that out. I'm such a dumbass. All right, 24. I forgot that X is like the second to last. Wait, third to last? Why is he third to last? So we really wouldn't be able to use these, actually. They're not big enough. I might as well just use the breadboard. That's gotta be... If you use a bunch of solder, let me go get that. Okay, so yeah, so this makes my life way easier. You see that? Because this, then I just have to lay out the breadboard, which I sort of have. Oh, crap. So in order to... Is there just a tool for breadboard layouting? Dude, fucking fritzing. Because if we do it with a breadboard... If we, Okay, well, let me just do it with paint. Or TL draw. I honestly don't see the difference. They both do the exact same thing to me. Where's the... Okay. So, this is the board. We have the Pico here. We have the driver. The driver. What else do we need? So then these are going to be... Or wait. So then this goes to there. This goes to here. Then this is going to be... These dots are going to be... Wait, what does this mean? This just means 2 of them. But these are going to be male. These are going to be male. And then what else do we need? We need... So now that's the steppers are done. Oh, the other question actually, though, is how big these holes are. We need to test with some... Where's my... Okay, so the great thing is 16 gauge solid core wire fits in great. Fits in perfectly. So I think we should be able to do this. Most of this you won't need 16 gauge wire for, so we're actually going to plan that out. So we're going to want voltage. Well, let's see. Maybe we put... Where do we need the 12 volts? The 12 volts needs to go to the stepper motor drivers. The stepper motor drivers and the ESCs. So if we put the... Well, I don't know how we're going to get a screw terminal into this thing. Let me go get the screw terminal. Okay, so let's see. It would be the best if it bridged the gap, but yeah. And maybe we could just use a 3. No, but we'd have to cut the legs off, but maybe. Oh yeah. There you go. Then you get 3. I mean, maybe just do it like. Maybe just do it like this. Dude, I want to use fritzing, but it's freaking paid for now. It's so stupid. And I'm not going to support them because maybe this is the best way. Yeah, and you just use that side for ground. Okay, so here's what I'm thinking. So on one side, you have the screw terminal, and it fits into the breadboard. And then you have the 12 volts there. So then you can have... Because the thing is, if you think about it, we're using 3 volts to go to way more places. So we should really have 3 volts here. And maybe we could just keep them separate. We could ground these. And then we could have this be 3 volts. And then this be 12 volts. Because then it goes like that. That. ESC ground. ESC ground. And then we also need the pins for that, though. So maybe... Well, you need the... That's the thing, is you need the pins for everything. Or, I mean, you need the Pico... Maybe the Pico should be in the center. Maybe that's a good idea. Maybe you do, like... Pico in the center. I don't even know if you can. Let me go get a Pico. Yeah, I don't see why not. So you just put this in the middle. And then put 12 volts there. Oh, but it kind of makes it annoying to connect to it. No, but actually it'll be fine because it'll be raised up by the But so then you could put the steppers here. We actually do need to count our pins basically because we have 60 and we need to make sure that everything fits. Yeah, and then we have 7. So this should be 7, 7, 20. The block takes up 2. Yeah, maybe this will be 12 volts. But the thing is, we can't really do that. And the reason why we can't do that is because I don't think that the traces on the back of this, I'm almost positive that what we'd have to do is we'd have to strip a big long wire and just increase that and just go along with it with solder across the whole length of the thing. Because otherwise it's just not going to be able to hold the current. Or at least, I don't know. Maybe I'm just going like way too overboard with this, but technically I feel like these aren't supposed to be able to take 10 amps. So what all do we have? We have encoders. And the encoders should be near the pico. It doesn't really matter where this. The only thing is that they don't. Oh, you could do. No, well, could you? I guess you could. You'd have like SDA, SCL, VCC ground, and then so yeah, you just tie them together. Because those are going to be 4-pin little female things. Is there really nothing besides fritzing that would help me do this? Damn, having a current requirement is actually so much more effort than you think it's going to be. Okay, I'm just going to do it on paper again. I wonder if I have graph paper. Whatever. Okay, this is the peak. All right, we're going to try to just lay it out. Just get something down with the pico at the top, like we already do. Okay. So this is going to be plus 12. Wait, actually, yeah. And then this is going to be... So then this pin, the 5, and this pin is here. And this is ground, and this is ground, or whatever. So then 23. So then this ends at 30. And this ends 40. So this one has 65 or 64, but this one only has 60. So we have only 20 pins left to do everything. And what do we need to do? Well, we need the power connector, so... I think that's the only way, is you're going to strip some real thick wire and just like... And then you'd have to shield it, I guess. Or you could just make it real messy and just go directly there, so not actually put it on a rail. See, you only need to go to 4 places. Yeah, so then you'd like go up and around. So this is like this. You go up and around. You'd have big thick wire there, and then you'd send one of these up to here. So another one up to these to here. And this could arc. It could arc, so it could go over other parts. Damn, this is like when you're actually designing your own, it's so much harder than copying other people. Oh, there we go. Okay. So the Pico's at the top. I don't know where the other stepper drivers are, but I mean, maybe we just don't need it to be on a flat surface. I feel like I do want it to be on a PCB-like thing. So yeah, so oh wait, but you would need or yeah, no, you could and then so I think the ESCs will connect directly so that I can do the thick wire thing. And then the stepper motors I'm just gonna go over the rail because like I don't think they draw that much current. So no, these come from here. And then you probably still need to do this. Why? Oh, because of the solenoid. Yeah, so where does the solenoid go? So now you need the FET. Okay, so here's the FET. And power goes to there. The gate goes up to there. And then the ground goes here. So you need to do this thing here like this. So you need to expand. But actually, how do you do that? I mean, the thing is, we haven't even, in the actual PCB, there's no consideration to current. But the thing is, what's going through this trace here is going to be like, dude, I don't know how other people do wiring at high current, because like, this is insane. I mean, how big does the traces need to be? Hecka big. Yeah. So wait,
The usual PCB design current will not exceed 10A, but some products are designed with power traces, and the continuous current can reach about 80A. Considering the instantaneous current and leaving a margin for the entire system, the continuous current of the power traces should be able to withstand 100A above. Today, eByte will introduce to you 4 methods of running 100A current on the PCB. The first method, trace on the PCB. If the current of 100A is to be used, the copper thickness of 4 ounce can be selected, the trace width is set to 15 millimeters, double-sided trace.
Dude, why do they always do this? This is
4 ounce
so
can be
goofy.
selected, the trace width is set to 15 millimeters.
Oh my gosh. But 15 mils, dude.
Double-sided trace, and a heatsink can be added to reduce the temperature rise of the PCB and improve the stability. The second method, binding post. Fix several binding posts that can withstand 100A on the PCB or product shell, such as surface mount nuts, PCB terminals, copper posts, etc. Then use terminals such as copper noses to connect wires that can withstand 100A to the binding posts. This allows large currents to travel through the wires. The third
I don't
method,
get that.
custom copper bars. It is a common practice in the industry to use copper bars to carry large currents. The fourth method, special PCB process. Some special PCB processes can easily achieve a small volume over current of more than 100A. But there are few manufacturers that can process it.
Today's video is sponsored by PCBWay. Let's make an old project even better. This right here is a very old project. It's very popular. We've made hundreds of these bus bars already for the headways. Headways are very popular among the audio community because they're cheap and they can put a ton of power. I once shorted out a cell, a single cell.
Generally above 300 amps. They're sagging down to 2.91 volts.
Whoa.
Oh my god!
Oh my god. That's insane. I mean, it's crazy that it literally becomes molten metal.
Do like a battery pack like this, for example, 64 amp hours, 8 cells in parallel. Well, you get the idea. You can get thousands of amps in here. Obviously, you know, they do sag, and so what they're trying to do in the audio world is trying to make a very stiff pack, a very stiff battery pack, so that the sag is minimal, and that way they can put out a ton of power, right? So we started with this design, and it worked really well, except that it had one drawback. At that time, I was talking to a few of these guys from the audio world. A lot of them, they don't know what they're doing, right? And so they couldn't really explain it to me what it is that they needed. And so now I am starting to understand what they need. That whole thing about creating a stiff pack, none of these guys could articulate that to me. And so this design is not the best one when you're trying to do that, right? And the reason is because even though these can carry quite a bit of amps, like I did some tests, this bus bar can carry 500 amps. This is not the best way. So let me explain to you. There's 8 cells here, and they're all in parallel. Now, those 8 cells go and transfer to the next 8 cells, and then to the next 8, and then to the next 8. So all the current is trying to go from this point to that point, and then from this point to that point, from this point to that point. So what happens is that it creates a hot spot right here, right? Because electrons are not going to go around like this and then come back. It's going to go straight right here. So really, what's seen the brunt of all the transfer of electrons is this right here, these 4 little spots. And when you look at the thermal camera, you will see that this section right here gets hot, and it's because of these 8, right? So because you're trying to make it the stiffest pack possible, then you need to be able to most efficiently transfer those electrons from cell to cell. And this design here is going to do that. And I'll show you, because the way this is designed, then there's 4 little connections here that connect the entire pack. But when you do it this way now, the cells are arranged slightly different. They're in parallel sets like this, the long way, right? So there's 1 set, 2 sets, 3 sets, 4 sets. And so now the connection doubles in area, right? Because now the connection is not 4 little pathways to connect to the cells. Now it's 8, because this cell will connect to this cell, then this cell will connect to that cell, and this cell will connect to that cell. So the current essentially goes from here, and then it transfers down here, and then it transfers here, there, right? And it does that 8 times. And so now, by rearranging the cells in this configuration, now you just increase the pathways. You doubled your pathways of electron of current transmission, right? And so that is why this design here, it's going to be a lot better than this one. And so what I've done is I've updated my design to allow for this. Also, I added the ability to put these little blocks in here, because then what people do is they put the cables in there, and they just cinch them up right here, and they just use an Allen wrench to put them in here, and then that way it's a lot easier than making ring terminals that require you to have a like a crimping tool and all those stuff. And it's just, so this way it's a little bit easier. Some people are using these, and that's the way, but you don't have to. You can directly put a ring terminal on here, 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 and you can put up to 8 cables. And that's what a lot of these guys are doing, right? Because they need a less amount of sag in their system, right? So let's go to the drawing board, and
I don't know what sag
I did to design this board that will make it a lot easier.
Yeah, this is what I want to see.
All right, so here is our drawing here, and
is he an I think he might be an easy EDA.
We put both of these together.
How funny is that he's using easy EDA, but he's being sponsored by PCB
as the top plate and the bottom plate. The reason for doing this is that it's a lot easier to order 1 file and 1 print instead of doing 2, right? And so this, 1, and you just break it in half, and then you use the top portion to the top and the bottom to the bottom. That's what works. So there we go. Let me explain here what's going on. This is the bottom layer, right? And if you get a 2-ounce copper layer when you print these, then it'll do more than enough to do 1,000 amps, because now it's thicker copper, and like I explained before, we have now doubled the amount of pathways that the current has to take through, right? So now this is going to be even a way bigger, stiffer pack. Now it was able to do 500 amps on now.
Okay, I think I'm gonna make food right now. I think now's a good break time. 5 hours in, and I swear I've done nothing today. It's all just remembering what actually needs to happen. I think a good plan is to, let's see, what time is it? It's already 4. I have 2 hours. That's good. All right, I'll be back. Yeah, I'm finally back. Exactly what I didn't want to have happen.
One ounce copper way before for a long time, but to get the stiffer pack that this design will allow is to do it this way, right? And of course, these little things here are for those blocks that will allow you to use 2 American wire gauge cable. You stick them in there, and then you don't have to do ring terminals. Of course, this is just an option. If you want to use this, they're going to be there to use them. But then you can use ring terminals here. These right here are for people that are not going to use this battery pack for audio equipment, for audio use, right? So there's less lower performance applications of this battery pack, and a lot of these guys are going to want to put a BMS, which is like a battery management system that is based on a solid state, right? So basically like some transistor-based relay switch that will turn on and off the power to this battery. And so in order to do that, then we'll use these right here. These are made for some these are terminals, screw-on terminals that can handle 180 amps, so 2 of them, 350, 360 amps, something like that. And then there's 2 on the negative, and then there's 2 on the positive. And so what that allows you to do, it's for a future board that I'm going to make, where then you screw it right on top of these, and they'll go into those terminals in there, and then it'll hold the secondary board higher above this whole thing, and then that board will have the BMS in there, and then it'll have the main terminals to go in and out. That the negative will go through the BMS and stuff. So that's what those are for here. But if you're using this just for audio, then you can just ignore those.
Dude, I don't even get what he means by use it for audio.
It just mirrors the bottom layer, because we just add another layer to carry the current. And here is going to be the 3D. And of course, if you were ordering this from our PCBWay sponsor, right, then you can choose whatever color you want. This is just blue, but green is usually the fastest and easiest. But you can do red, white. You can get a white one. White one looks pretty cool. Yellow, black. Black also looks pretty cool. And then I chose purple because I had the green one, and just to distinguish the 1,000 ounce from the 500 amps, the 2 ounce copper to 1 ounce copper kind of thing. So these are the ones that we're selling on Jack 35. You can order this there. But if you want to make a custom color, then you can just go to PCBWay.com and order yourself through the link on this video. There's a project.
Who is this guy, bro? Pretty cool.
Heavy copper on circuit boards can be essential for high current applications and are useful for removing heat during board operation. But that same heat dissipation can be problematic when populating boards, as it takes a large amount of power to heat up the same areas to be soldered. Fortunately, there are several ways to address the challenge of soldering on heavy copper circuit boards.
I never thought about
thermal
that.
reliefs in the design of the solder pads. Limit the surface area connecting solder pads to planes of heavy copper. By using thermal reliefs, you decrease the surface area that connects the solder pad and the plane, increasing the thermal resistance. Increase the time and heat when reflow or wave soldering. Thick copper PCBs have a greater thermal mass that takes more time to heat up and cool down. During assembly, the temperature profile can be adjusted to slowly heat up and cool down.
That music is so annoying. I trust this guy. This guy is...
In this video, we are going to talk about designing boards with very high current power supplies. And by very high current, I mean power supplies that can deliver hundreds of amps or even over thousands of amperes. I'm not an expert for this topic, so I had a call with Steve. I recorded this call, and that's what you will see in this video. I really hope you will find it interesting and useful. Here is my call with Steve. We are going to talk about high current power supplies. And when we say like high current power supplies, what does it mean? What kind of current we are talking about?
So 500 amps is probably where it starts, and there are plenty of Intel processors now that are at 500 amps or above. And there are a lot of GPUs that are well above that. So current state of the art is probably in the range of about 1,000 amps. There are a few companies that are doing 100 millimeter ASICs that are in the 1,500 amp to 2,000 amp range. But I would say the current state of the art, we could probably consider that to be around 1,000 amps.
Wow. And what kind of voltage we are talking about?
Most of these are around 0.7.
0.7.
0.7 volts.
Mm-hmm.
Dude, what? 700 watts? That's insane. Whoa.
Are there also some?
Is that like a Xeon?
I haven't seen any higher voltages. There are some at 0.6. They are, trying to drive that down, but the noise margins get kind of small. So right now, most of them are still in the range of 0.7.
Mm-hmm. Okay. So if someone would like to design this kind of power supply for high currents, what they need to be careful about? Do they need to care about like copper thickness, or what is important?
There are a few things that are important, but one thing is that it's really important to minimize the inductance between the power supply and the ASIC, because that's going to result in the number of decoupling capacitors that you need. And so first is how close can we get the power supplies to the ASIC? That's probably the first consideration. There's probably also the second and third consideration. Once you get through getting the power supply to be as low inductance as possible and as close to the chip as possible, then after that, then you can start to look at other effects. One of them maybe is thermal, although I think thermal is not really the biggest issue with the power supply itself, because if you think about it, the power supply is 98% efficient, on that order in most cases, well into the 90% range. So a kilowatt, you're going to dissipate maybe 50 watts or 20 watts into the power planes. But you have 1,000 watts dissipated in the ASIC that also has really good copper connections from the balls into the power planes.
Oh, so basically the heat will flow from the chip to the flow from the chip to the power supply, then from power supply.
Exactly. So they all add together, but I think you're getting a lot more heat from the ASIC into the board than you are from the power supply into the board. So that's kind of the lesser problem. And of course, the heat goes the other way too. So the heat that's dissipated in the VRM gets sucked up through the balls of the ASIC also, right? It goes out through the cooling system that's sitting on top of the ASIC. So it kind of goes in all directions. Some of these boards, the boards themselves are water cooled. The devices on the boards are water cooled, but not too many of them. We're just starting to see that. Now, Vicor was looking at the possibility of building on-package VRMs. In fact, they did it, right? They actually do offer on-package VRMs. And that goal is really just to keep going along the thought that says that we need to get the VRMs as close to the ASIC as possible to minimize the inductance.
So basically, you don't you don't design this kind of power supply by yourself. You place a module on the board close to the chip, and that's generated. And,
correct.
And when you say it like water-cooled, so you say water-cooled boards or PCBs or water-cooled heatsinks, or what do you mean?
Both. In fact, at PicoTest, we're actually working on water-cooled printed circuit boards now, very small ones for our probes. Because we do have very high heat concentrations actually in probe heads. And how do you get the heat out of that? The only way we can get the heat out of a tiny little probe like that is liquid cooling. So you'll see actually PicoTest is going to come out soon with water-cooled printed circuit boards.
So the water flows inside of the PCB?
Yeah, we're actually running two parallel paths right now. One is to have water channels embedded in the heavy copper inside the circuit board.
Whoa.
And another one is to bring copper coins through the printed circuit board to a backside manifold. And which way is going to turn out to be, optimum from a cost performance standpoint, I'm not exactly sure. But we are actually looking at both of those options. And when you get to these high power systems, that becomes really important too, is how do you get the heat out? And mostly it's going to be water cooling.
So is it like normal water, or is it like some kind of special water? Or?
There's liquids in it. Think of it more like an antifreeze, right? So there are chemicals in it, but it's a liquid cooling system. And
so it's not it's not going to cause corrosion, for example, or?
No, because the water itself is isolated inside the channel. But right now, a lot of computer boards are water cooled. The ASIC itself, it's pretty common to have water cooling systems for those. Yep. And they circulate water, and they have a radiator, in the front, and then they got big cooling fans that blow through the radiator. So that's kind of common.
That's what I thought, but I never really knew that you can flow water inside of PCB.
Well, yeah, eventually you have to. And what it is that they say, necessity is the mother of invention, right? So you do what you have to do. Of course, Intel is looking at other directions too. Intel is looking at actually putting the power supply onto the ASIC. And if you put the power supply onto the ASIC, well, that's about as close as you can get, right?
So you would power up chips with 12 volts, for example?
Yeah, exactly.
Okay.
Whether that's ideal or not, I don't know. At 1,000 amps, even 12 volts is almost 100 amps, right? So it's still an awful lot of current that you got to move around. And now you're moving that around on the package. It could be more beneficial to get the voltage up, which is why you're seeing 48 volts now in a lot of these high power applications. It's to get that current down. And also since the power supply input is a negative resistance, and that's a term that people struggle with. But think about it. If a switching power supply has a constant output power and high efficiency, then the input power is constant also. And that says that if I raise the voltage and have the same power, the current had to go down. And if I have a current that goes down when voltage goes up, it's a resistor, but it's negative. And that becomes really important because negative resistance is actually the core of an oscillator. And that's something that, people studied for a long time. In fact, it's probably one of the most researched doctoral thesis topics is the Middlebrook criteria negative resistance oscillation. So inductance on the input side of the switching converter will tend to oscillate as a function of the negative resistance.
All right. They are way out of my depth.
Hi, it's Twitter question time. Let me know. Leave it down in the comments down below if you want me to do more of these. I do, of course. Follow me on Twitter. None of that X-rubbish. Follow me on Twitter, and you can ask me questions anytime, and I'm always answering questions there, but I thought this one might just make an interesting video. I have covered it in bits and pieces in previous videos, but we'll go into it a little bit more here. It's a simple question. Abhinav, sorry I'm butchering that pronunciation, I'm sure, but he asks, he's designing a PCB trace for 70 to 80 amps, so a substantial amount of current. How should I design the trace from the connectors to a MOSFET device for this current rating? Is it possible to use only one layer? And it's a through-hole device. So we won't go into like the routing and all that. So is it possible using only one layer? So I presume that he's asking that because, well, he's got other routing constraints and doesn't want to chew up the bottom or internal planes, assuming it's even a multi-layer board. It might just be a double-sided, don't know, because it is a through-hole device. So it could only be a double-sided board, but you don't know. Anyway, the first thing you want to do is you want to, basically when you pass current through any conductor, of course, copper is on the PCB is a conductor. And of course, Ohm's law, if you've got resistance at a certain current, it's going to drop voltage using Ohm's law. So that could be a problem, but we won't go into the design aspects of like the voltage drop and things like that. But that is one of the things that you have to consider in the design. But also the power dissipation is going to heat up I squared R losses. The current squared times the resistance of the trace. And you can have a big giant plane, it's still going to have resistance on it. And you have to sort of like take that into account. One of the things you really need to do with this is like there's a few rule of thumb things. You can have little, simple charts and stuff like that, which give you a rough trace diameter for a certain current and stuff like that. But there's much more engineering and science actually behind it. So you really need, at a minimum, you need a PCB trace calculator. And the one I use here, I'll show you, it's Saturn PCB design. It's free. You can just download it. I'll leave a link down below. And it's got all sorts of stuff. Like it's got tons of stuff. I won't go into all the stuff it's got. But one of the things it does is it's got conductor properties here. So we can put in the various parameters up here, and then it will give us the conductor DC resistance, how much resistance that trace has got. So we can use Ohm's law. We can calculate the voltage. Well, no, it already calculates the voltage drop for us. There it is. And the maximum conductor current that it's capable of. But there's a lot of stuff that goes into this. So let's have a look. There are three major things that dictate how much maximum current a particular PCB trace.
What does that mean, though? What is the maximum
diameter of the trace? Now, obviously, if you've got a little tiny thin, 10 thou trace, it's not going to carry much current at all. So the thicker, the wider trace you make it, the more current, because it's going to lower the resistance. It's going to have less I squared R losses. It's not going to heat up as much. So that's the first thing. But not all copper's the same. So the second thing is the thickness of the copper, because PCB comes in different copper thicknesses, and none of this metric rubbish. We want imperial for this, because we work in imperial. And when you order your PCB for manufacture, you should be specifying the copper thickness of every layer in your PCB stack up. And I've done videos on stack up in, not specifically on that, but I've covered it in previous videos. But basically, every piece of copper in your, if it's an 8-layer board, you've got 8 layers of copper in there, and you can individually specify the thickness of each layer of the copper in your PCB stack up, it's called. So if you've got, if you want to run a real heavy current on one particular plane or one particular layer of your board, then you can specify, okay, I want much thicker copper on that layer, and the manufacturer will do that for you. And if you don't specify any of this, they'll just give you this standard stack up, which might be 1 ounce copper which is 35 micron thickness. You can change it over to metric. There it is there. 1 ounce copper is your standard thickness, but if you've got a multi-layer board, they'll often use ½ ounce thick or maybe even ¼ ounce thick copper on those inner layers. So if you don't specify it, the manufacturer is just pot luck what you actually get. You won't get more than 1 ounce because copper's expensive, right? And they want to keep the cost low. So your standard board, you won't get any more thickness than 1 ounce copper.
Yeah, the etch time.
On any of the layers on your board, unless you specifically ask for it. Then you might jump up to, usually you jump up to 2 ounce for that. So it's twice as thick. So it's going to be lower resistance. And once you get to 4, 5, something like that, that's really thick right? Really thick and expensive copper. And you do that for really exotic, applications. If you want really high current board, but it's got to be really dense, for example, and you can't make your trace really thick because you've got real tight routing in there.
Wait, but why does it only say 1.6 amps?
You could even get an exotic one even thicker than that. And the third parameter, which is not as important, but it matters, is whether or not the copper's on the top, external layer of the PCB, so the top of the bottom, or whether it's in the internal layers of the PCB, because they have different thermal properties. Because if your conductor is dissipating heat and it's wedged in the middle of it, sandwiched in the middle of the board like this, fiberglass
this is a cool tool,
right? So the heat can't get out. So the temperature will that heat will get trapped. It can't escape. So it'll get hotter, which will increase its resistance. And right, well, it doesn't run away, but right, it's going to get higher resistance the hotter it gets. Whereas the outer layers, they're going to cool more easily. And also the solder mask over the traces can make a difference as well. If you've got solder mask over there, that's an insulative layer on your copper. So that can matter as well. But generally, unless you're really getting down to the nuts and bolts of it, there's only two major ones: the thickness of the copper and the width of the copper. But the layer stack matters too. But it's not like a copper trace just suddenly bursts open and catches on fire or breaks, because you can actually use a PCB as a fuse. A PCB trace as a fuse. And there's a bit of art and science that goes into that. I might have even covered that in a video somewhere. Can't really remember. It doesn't just suddenly magically stop carrying current. It just gets hotter and hotter, and it might delaminate from the board. It might, it glows red hot or whatever, right? So it's all about the temperature rise that you're willing to tolerate in your design. Now you can see here, this is one of the parameters, 20 degrees C temperature rise. Me personally, I prefer
I remember GPT telling me
temperature rise if I'm doing these calculations, but there's no reason for that. It's just my own personal rule of thumb for a 10 degree C temperature rise. And then there's ambient temperature as well if you want to get really fancy-pantsy, okay? So let's actually start using this to do a basic thing. Let's say we've got standard 1 ounce copper here, okay? And we've got no plating, okay? The plating is another thing that matters. It's not only the solder mask over the top that can impact, but most boards are usually solder mask over bare copper, or SMOBC. So you can just say bare PCB like that, okay? And we're going to use external layer. So we've got an external PCB layer here, and we've got a bare PCB, which will have the solder mask over the top. It doesn't really matter whether it has the solder mask. In fact, they don't even have the solder mask in this calculation, but technically can make a little teensy bit of difference. So 1 ounce copper and 10 mils is ridiculous, right? So let's go for 100 thou, right? 100 thou trace, 100 mil trace. Not that millimeter rubbish.
Small.
And the conductor length here, we don't know. So it depends on your particular layers. So the total resistance will depend on the conductor length, of course.
Right.
And then that will determine the voltage drop, which you're willing to tolerate, because that might be part of your electrical design rather than the you've got two issues here. You've got electrical and thermal as well. And you might even have high frequency stuff. That's why they've got like skin depth over here and skin depth percentage. Anyway, we definitely won't go into that. We're talking about like DC current. So 100 mils, plain, present, no. Parallel conductors doesn't matter for purposes here. Ambient temperature, we're just going to run that. It's an external layer. So let's solve that, okay? There you go. It's 5 milliohms there for a 100 mil wide trace, and that can do a nominal 3.28 amps. So generally so if you try to put 3.3 amps through a 100 mil wide conductor, and we can convert that to metric for you metric fanboys, 2.54 millimeters, there you go. It's going to, at 3.3 amps, it's going to rise 10 degrees Celsius if it's on the outside of your board. Is that acceptable to you? I don't know, right? So we're talking 80 amps here, okay? 80, what was it, 70 to 80? 70 amps, so let's take 80 amps, metric, right? 25 millimeter wide trace, right? A 1 inch trace. Let's actually solve that. With 1 ounce copper is only going to do 12.6 amps. So we're going to have to, let's double it to 2 ounce copper, okay? So twice as thick copper. So we go from 12.67 to 20.9 there. It's not quite doubling. If we go 4 again, will it get to 40? No, it gets to 34, right? It starts to limit it. So you can see that you've got like really thick copper here for a 1 inch wide trace, okay? So this is getting quite an issue. So he talks about like putting it on a single layer. You're really starting to push like 4 ounce copper. That's pretty specialized. You're going to, some cheap PCB houses just won't do that. And you won't get this on your regular, your $5 prototype board, right? You're not going to get that. They might give you ½ ounce copper, and then you're only limited to 8 amps. So really, we need double that. And a 25 millimeter wide trace, like a 1 inch wide trace, you probably don't want to make it any wider than that on your PCB, right? That takes up a massive amount of room. So you might want to actually, put some solder coat over the top of that, right? So you can get a tin plate, for example. So, but unfortunately, right, this plating thickness doesn't actually take into account like the tin plate process. That's really hard to control. So if you go to your PCB manufacturer, I want a tin plate on that, please. Then it's the control thickness is I've done a dedicated video on that and how much difference a tin plate actually makes. I've done some practical experiments on that. I'll link it in. But you can't really control that, but you might be able to tell them to actually plate it a certain thickness or whatever, right? But once again, this is a big increase in manufacturing cost. PCB manufacturers will do absolutely anything. The good ones will. They'll bend over backwards. They'll do anything you tell them to do. They'll charge you for it. Okay. So if we did that, 1 ounce plating thickness, we're still only at 40 amps, right? We still have to double that. Even go like we're still not there. So let's just go to a random PCB manufacturer here, and you'll notice that they go from 1 ounce up to 13 ounce copper.
PCB weight is insane,
but there's trade-offs there. They actually tell you minimum track space requirements and all that sort of stuff. But they say they can do 13 ounce, and they can. But generally, they're only going to go up to, I think this manufacturer only says like 3 ounces, kind of like our standard process. So anything over that, they're going to like order the material special. They may not have it in stock, and it's going to cost you an absolute fortune and all that sort of stuff, right? And then you've got the surface finish over here, okay? And generally, you're going to get a what's called a hassle, right? Which is a hot air surface level finish. So they just put basically solder coat. That's basically what it is. And then you're familiar with like the gold flash boards, the immersion gold. And I've shown my boards before that they have come with immersion silver, for example. You can get immersion tin, and you can get there's all sorts of stuff, and you get nickel plated ones and all sorts of stuff, right? Plain copper. You generally, as I said, if you want, here's an example. If you want your traces to be coated with solder coat like this one here, okay, yeah, that can increase your current handling capacity, but it's not really a controlled process. They can't really, it might be hot air finished. You might be able to see like a few bubbles and stuff in there, right? It's not really a controlled process. You can't really guarantee what your resistance is going to be. It's just hot air, so it's whatever the process just happens to be. But it can increase your current. Now, the way you do that is to remove the solder mask. You have to remove the solder mask over that trace. Otherwise, when they do the board, you're just going to end up with that bare copper. Because as I said, the copper under here is just bare copper. It's SMOBC, solder mask over bare copper. I'll show you. See, if I scrape away that solder mask there, you can see that is just bare copper underneath there. So the process that they do happens after they put the solder mask on. So if you want your traces coated like that in whatever surface surface finish that you actually choose here, whatever surface finish you choose, if you want that coated, you have to leave the solder mask off. So back at 1 ounce copper here, like I'm being tight-ass, Dave. I'm only allowing for a 10 degrees C temperature rise, right? So if we go to 20-degree rise like that, okay, you go from 12 to 17 amps there, right? And then if you go up to your 4 ounce thick copper, you know, but you're still not getting a huge amount extra there. Like, I'm willing to make it go 50 degrees above ambient, so your PCB trace will be at 70 degrees, right? Remember, this is temperature rise above the ambient temperature, okay? Solve. We get to our 80 amps, okay? So if you want to do this single layer and you're willing to fork out for 4 ounce copper board material, and you could maybe get it, it's going to rise 50 degrees C. But once again, these are actually calculations. There are formulas for this, and this is where it gets it from, but it's based on really empirical data, and this goes on, like it tells you here, this is based on the IPC standard 2152 with modifiers, and you have to go read the IPC standards. There's actually 2 IPC standards that cover this. There's the earlier 2221 standard here, and I just Googled, the first thing I got was this Altium article here. Anyway, they linked to some calculators, I'm not sure which ones, but yeah, basically there's 2 different standards that'll cover the same thing. The IPC 2221, and they note here that the 2221, that was based on charts in the linked articles. So someone way back in the early days did some charts, like actually old school charts, and they've got them in the standards. You can look it up. They're hand-drawn charts or whatever, or they, you know, these plotted charts, and that's where everyone's gotten sort of this data from back in the old days. But there is another standard, the IPC 5122, which is more accurate. I don't remember the exact details. It's been a long time since I've looked at the standards in this regard, but just realised that the formulas are kind of based on sort of like experimental, you know, measured data. So it's a bit how you're doing, but it's the best we got. Now, interestingly, let's see if internal layer actually makes a difference here, and it doesn't, right? Internal or external layer actually doesn't make a difference here, which is interesting because in practice, it kind of sort of does, although once your board's heated up, you know, like it depends on your thermal, but the physical part of your design matters. Like if you've got a fan in there and you're blowing over the board, for example, the outer traces, yeah, they can get better thermal properties than the inner traces in there, but it's obviously not taken into account in the IPC 2152 standard. And it's going to matter whether or not whether your trace is adjacent to like a big plane, for example, because you can get conduction between your little trace and the tiny little thin pre-preg in there. There's not much different thickness between your trace on, say, an inner layer and the pre-preg, for example. If you've got it on the outside, it's a bit further apart. And this is why they actually have a plane present thing here, right? So if we click yes here, then this is our current carrying trace, and you can see it's jumped up. It's quite substantial. It's jumped up from 78 amps here for, once again, a 1 inch wide trace for a 50 degree C rise, you know, and then it jumps up to 121 amps. And we're not running the current through that plane. It's not going through this big blue copper plane down here. It's purely the proximity. This is why they give you, yeah, here it is, distance to plane, right? 10 mils here. So metric, you know, it's only 0.25 millimeters away. So if we actually go from 0.25 millimeters to 1 millimeter there, it should, like, it goes up a bit, right? Because this is all thermal conduction through to the plane. Even though the current's not running through that plane, simply having the plane present, it's more better. Anyway, as you can see, like, there's a lot of stuff involved in this if you really want to go down the rabbit hole. But in answer to the question here, is it possible to use only one layer? And the answer is probably no, not really. Not unless you use like massive traces and you allowed for, you know, a huge temperature rise and stuff like that. So yeah, you'd be using, you know, at least 2 traces, possibly part of your internal plane as well. To get 70, 80 amps is quite substantial. Or you could, as I said, you could like tin plate, you could solder plate the top of those traces, and that increases.
Yeah, that's kind of crazy. Let's see what else is in the video.
Manufacturer. And then if you really need like a compact design and you don't like have layout room on your board, you might consider like a bus bar approach. I found one example here. You can see that this board uses these physical bus bars, which run right across the board like this. And of course you can get, you know, you can make those thick as, right? And, but you know, you have to get those like custom manufactured, and you'd have to go to a company that manufactures those. So, you know, a specialist manufacturer that makes those. But yeah, bus bars, they're, you know, quite common on like really dense, you know, highly populated boards. So it's definitely worth considering something like that. Like this one here's got like 3 ones. In this particular case, it's carrying power to like all the devices across the board like this. But, you know, you can get just one.
Wait, but you know what I just realized? Is that, whoa. Squirrels, bro. What the fuck? Silly bro. So we don't we don't actually have to run the ESC to the board at all. I don't know why I didn't clue into that. That thing is literally just going to go straight to the power supply. That simplifies things considerably, because that means that the only thing that really needs to be on the board that carries high current is the MOSFET. That does make things easier. I didn't really think about that.
Today I'm going to teach you how to find
Okay, hold on. I'm gonna clean up this food. So basically, I guess the reason why you say basically how much you want the thing to heat up is because basically, well, I don't know what kind of calculation they're doing, but the only reason why I would reach steady state is that basically the power loss across the trace or whatever ends up equaling the dissipation rate. That's the only time when the temperature would be constant. Otherwise, it would just keep increasing. So the main question is basically, well, let me look at the. So yeah, so the ESCs we're actually gonna just not even. We just don't even need this. Like these can just go directly to the power supply. It's actually way better. Oh, and actually, now that I'm thinking about it, we might want to use this third pin here, which is fine. But we might want to just, because I don't remember if that's 5 volts or 3 volts. Let me see, do I have the ESC in my bomb? When did I put this in? Oh, that's the oh yeah, I know what that is. This is old, man. This is real old. Yeah, here's the ESC. Oh wait. Does this say the pin out? Yeah. Trying to. Where does it say what the output of the? Maybe you can just give it. Where's the pico pin out? I always forget if it's V bus or V. I think it's V sys, and you give it 5 volts. But I can't remember. Wait, but why don't I just use a voltmeter? We could just use a voltmeter really quick. You take the ESC. You don't plug in any of that. Okay, so let's do that. Oh, but the power supply is freaking bolted to that thing. That's okay. Or it's not, but it. Yeah. Actually, it's not. I just realized that. It's not. Okay. So we're just gonna. Let me get the. Because it'd be really handy to be able to use the. If there's this 5 volts regulator on the ESC, we might as well use it, right? So we need to hook this up. That means I need my friggin' screwdriver. Okay. So let's just put this in. I was sort of under the impression that stranded would be better, but apparently it's not. Okay. Now we just need to take. I'm pretty sure it's 5 volts. I'm also pretty sure that that is what you want. Okay, so you turn this on, and you turn and you plug this thing in, and we should see 5.4. Let's see. How do I power my Raspberry Pi Pico W without using the USB? I think it's VSys. 5.5 at the maximum. Okay, so that's perfect. So then, all right. So we are going to use this thing. So, where's my mouse? I don't need my mouse. So, Jeez, man, this takes way longer than you think it's gonna. And the question is, you kind of want to tie these together, right? So this is going to be 5 volts. Okay. I think, though, that you may burn it out if you connect both the USB and the sys. Is it a problem if the USB and the VSys pin are VSYS are connected at the same time? Oh, okay. Okay. So then we're good. And we do want to just delete basically all of this because this just goes directly to the how the hell do you, oh, there you go. Okay, yeah, so these ESC's 5 volts is tied together. Alright, so this goes to the power supply. These do get the 12 volts. Alright, so let's draw this out then. We need, what's the diode? I think it's 1N504, so let's just add that. A shift F. 1N504. What is it called? 540? They recommended what? This seems weird. There we go. Is it through hole? Yeah. Okay, so then this thing needs another terminal. Hold on, let me get my mouse. We're almost done. So then we just need one of these. So, okay, so, let's just, I forget, but I'm pretty sure that's the gate. Then this goes to BCC. What the hell? And then this, so I think that's the source. And then I do not know what decoupling capacitors are at all, bro. No idea. All right, so that's what I think it is. But I think I think we're doing this, right? So then we take all this. And this is going to be solenoid. All right, not so bad. Okay. Oh, wait, and then we did not. Oh, we did. Okay, so let's save this. And let's import the changes. Okay, now where does this go? This goes out here. And these diodes. Or maybe. Oh wait, we want to get that close, right? Move this away. I don't know, what do these go to? Is that 12 volts? I can't remember. I feel like that's just ground. That's ground, right? Wait, but pin one of it doesn't have numbers. What is what? That's it, dude. I want to know which is which. But anyways, none of them are tied to ground, but this is ground. Wait, where am I? I'm so twisted, bro. Wait, where's the other diode? Honestly, we could just put this shit anywhere. The auto router will figure it out. Just do it, bud. We'll need to fix the design rules, right? That's a big thing that's left to do. Let's see what's up with the. Oh, okay. So the other thing to do is use the calculator to determine trace constraints. Now the question is how much temperature increase can I really do? Okay, because it's really just the transistor that it's going to need a big trace. Yeah, it's kind of sad that there's no additive process to make PCB traces. Yeah, so what if we did this? So wait, where does the... Oh, yeah, okay, so wait, what if we took these guys and we moved them real close here? And then unroute all. It's so awesome. Okay, so... Yeah, that's... Oh, wait, is this the... That's the gate? That's... Okay, that's V12. And then this... And what is this? This goes to the... Okay, so this needs to go like that. And maybe we can do this. We basically just want to make sure that the... That's V mode. So this is plus 12. What the heck are these going to? These are going to the sensors, right? But then why are they getting 12 volts? That must be ground. Dude, I gotta get ready to go. This is... Wait. This is ground. And why are these getting 12 volts? I think that's wrong. So the 4-pin, this thing, yeah, this is not getting... This is getting 3.3 volts. So we need a I think you're just supposed to do this. Oh wait. Wait, what's going on with... Oh wait. Wait, we had one. Oh my gosh. This is insane. Oh my god. What the hell, bro? Wait, but that doesn't do anything. How do you access the layer? There's something under this thing. I don't even want to deal with that. How do you get to that? You can't select the parent. You can only select the text. How fucking silly is that? These editors are so annoying. Okay, but how did we do that? We just okay. It's just like a special one. So you just do this, and you just change this to 3v3. And you copy this, and you place it here, and you paste it here. Okay, and now this goes to that. As does, yeah, that. Wait, did we actually do that? I guess we must have. 3v3. Is this, I guess it's not case sensitive. It's probably for the better. Alright, so now we auto-wrote it. Okay, so we get the 12 volts, this, and this. What does this go to? That connects to ground. There's a via there. What is that? Oh, okay. So 12 volts comes in here. It goes over to there. This goes over to there. So where's the this is the transistor. This is the gate source. And it flows through here. Then where does this connect to ground? Or this doesn't connect to ground. This just connects to that. And what does this connect to? No, that's ground. Oh, so it goes like this. Because we kind of want... We're trying to make the... Because I'm pretty sure the entire loop needs to be able to handle the current. So you want to make the path that is actually going to have high current go through it be short. Okay. Right, because these connect to ground. All right, so wait, okay, so there, that's good. That's good. Because now we can make this track, oops. I don't think you can, I think you have to do it all with rules. But now this is going to be a big old thick track. The problem is you don't really have that much room. Kind of a problem. Where's that, yeah, 10 amps. Yeah. 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 Sure. So wait, if I change this to 15, does it? Okay, it changes. See, that's the crazy part. 9? What happens if we change? Let's just like see what happens if you take design. Is it design? Yeah, this needs to be 6. Wait, 6 or was it like 9? It was 9. Look what happens if I change this to 9. It's totally unsatisfiable. 9 millimeters, dude? That's like so big. And I don't even think our board setting, somewhere in here we probably have the I mean that's just so goofy. Maybe if you had 4 layers. Let's see. Oh, there's the import change. Can I move that? You can't change this? How do you change it to it's all just JSON? I want that software though. Because, okay, wait, hold on. Oh, wait, 3 for external layers in air. Okay. So we actually need it to be 3. So let me, okay, there's that. And then this is for 2. Oh, wait, let's say we can deal with a 20. Okay, so we need to make a 2. So let's change this design rule to 2.5. So these are the nets. Okay, cool. All right, so now unroute all. This is going to be like the last thing I do because I got to go. Oh my god, that's the most annoying thing. It's still like, look, dude, I can't do this. What 7 failed? I don't think that was the only thing, though. Oh, and we need more clearance, too. Ay, bro. Failed 11 with 5 vias. Alright, so we couldn't get signal. What else? That's the only line I see, though. Oh, all of this? Do I just have to move this out? Oh, okay, wait. So we need to just... Alright, but... So that's 4. Oh, and this is where all the other ones come from? So if we just... Alright. So I'll keep working on this. I totally forgot how much time just actually getting the electronics down takes. But I feel like I know what's going on now.